All right, welcome everyone. The sign-in sheet is going around. Make sure you get it. I'm Simine Vazire. I'm the lecturer for the next couple of weeks of this class. And before we get started, I'll tell you a little bit about myself and my background so you know where I'm coming from. So as you can tell from my accent, I'm not Australian. I grew up mostly in the US in California and moved here in March 2020, which was an exciting time for all of us, but maybe an especially exciting time to move countries. So I got my PhD at the University of Texas at Austin in social psychology, social and personality psychology. And I worked mostly on basic research in social and personality psychology for years. My research was on the accuracy of people's self-views. So how well do we know ourselves? How well do we know our own personalities? Do other people sometimes know us better than we know ourselves? Sometimes it touched on things like 360-degree feedback and how does it change our self-views when we find out how other people see us and so on. I got my PhD in 2006, and my first job was at Washington University in St. Louis. And as I was going up the ranks there, going up for tenure, the replication crisis hit psychology around 2011. You've probably heard of it, but if not, you'll be hearing about it a bit more from me in these next few weeks. And so I started shifting my research to whether our research is solid, whether our research practices are good practices, whether the way we collect data, analyze data, interpret it is valid. I was already teaching research methods anyway, so it was kind of natural for me to start kind of questioning those things more. And I also became a journal editor. So since about 2011, I've been an editor at 7 different journals. And so a lot of journal editing is actually applied research methods, right? You're reading papers and evaluating whether they did the research correctly, whether they're making correct inferences, whether they're generalizing appropriately, et cetera. So I really threw myself into journal editing, and I love doing that. So I spend a lot of my time kind of reading papers very closely, critiquing them, evaluating whether the authors are exaggerating too much or drawing the right inferences, et cetera. And I continue to teach research methods. I moved to another university in California, University of California at Davis, where I taught there for many years before moving here to Melbourne. And I continue to do a lot of journal editing. I've also just become more and more active in this reform effort in the wake of the replication crisis in psychology, trying to improve our research methods, our publication practices, and including how we apply our work outside of academia. So are we responsible in the claims that we're making to the public, in the way that we represent the applicability of our work to public policy or everyday life, et cetera. So I've done a lot of kind of science communication around that. I loved Twitter. I'm very sad that it's gone, because academic Twitter and like especially social psych Twitter, I think was a really big place where we would kind of discuss these issues as a field. And I think the whole replication crisis and the reform movement that came out of it wouldn't have been possible without social media. So today, the next few weeks, we'll be talking about how do we assess when a claim is valid? And so I've taught this to many different levels, PhD students, undergrads, master's students, et cetera. And even though different people have different paths where they go after this, it's always really, really important to be able to assess whether a research claim is valid, whether research design is valid, whether you're going to be producing research yourself or evaluating other people's research and deciding whether and how to apply it. And this question of how do we know what research to trust is really important. And it's especially timely now because just in the last few weeks, there's been a couple of cases of fraud that hit really hard in psychology in particular, and especially in marketing in the area of nudge research. So you might have heard about this, maybe not, but it's made the headlines. There's 2 different researchers, Francesca Gino at Harvard and Dan Ariely at Duke University, both of whom have done a lot of research on nudging. They're both marketing professors, and their research has come under question to different degrees. So in Gino's case, Harvard did an investigation, retracted 4 of her papers, and placed her on administrative leave, so leave without pay for 2 years. Just last week, she sued Harvard for $25 million, as well as suing this blog. So the initial evidence of questionable results in their papers came from this blog, Data Colada, written by 3 business school professors. And not this blog post actually, but this was a blog post about Dan Ariely's a study of Dan Ariely's. But they've also written blog posts about Francesca Gino's work. Of course, their blogs are focused on the work and their questions about the validity of the work, but she's suing them for defamation. So the whole field is watching very closely what's going to happen, because if you can get sued just for raising concerns about the scientific content of a paper, it was nothing about Gino as a person, it was just about the work. That's very in my opinion, very bad for science. It becomes very hard for us to critique each other's work. So we're all watching very closely to see what's going to happen. But it's interesting for this class that a lot of this research is actually has formed the foundation of some public policy in different countries. There's a great thing that we might listen to a bit of it next week. The National Public Radio in the US did a segment on these cases, and they interviewed Michael Sanders, who was the head of the nudging unit in the UK. And he talked about how he made important decisions and spent lots of resources and time and money on studies based on the work that's now come under question, in some cases been retracted. So it's, as I mentioned, it's made the headlines. There were already questions about nudging research before this, so there were competing meta-analyses, and we'll talk about those a little bit next week, about how much we should trust nudging research, which part, I mean, obviously nudging research is this huge broad field about how we can change people's behavior or attitudes with subtle things, like where we put a checkbox on a form or where we put food in the cafeteria, et cetera. So there's a lot of questions about that. And obviously it's not all one thing. So there's parts of nudging research that are solid and parts that are weak, just like any other field, right? There's going to be some research on cancer that's good and some that's weak and so on. And for all of this, the question is, how do we tell what we can build stuff off of? And there's even some academic papers specifically about this question of, like, how do we tell what parts of the science of behavior or nudging research or social psych more generally is solid enough to be applied to bettering the human condition. This is one of the meta-analyses claiming that there's not evidence for nudging as a whole after adjusting for publication bias. This is one of the competing meta-analyses. And then this is one of the most recent Data Colada blog posts. And the reason they called it cluster fake is because it turns out that there's a paper where Ariely and Gino are both co-authors. A few years ago, they raised questions about study 3 in that paper, which Ariely admitted that he was the one who was in charge of that study, but he claims that he did not commit the fraud, but he admits that it looks like there was fraud committed in that study. And then later, a few years later, just last month in June, they discovered that study 1 of that paper looked like it had fraud in it. And so it looks like 2 independent studies in the same paper had fraud behind them, probably for 2 independent reasons, because all the authors agree that Ariely was the main person responsible for study 3 and was not responsible for study 1. And it's pretty clear there was fraud in both studies. So it's this bizarre, and ironically, the paper was about how to get people to be more honest. It was the finding, you might have heard about it. They claim that if you get people to sign an honesty pledge at the beginning of filling out a form rather than at the end, so instead of saying at the end, I promise that everything is true, you write at the beginning, you say, do you promise to answer everything truthfully? And they sign there. People are more honest. There's no evidence of that. It might be true, but the evidence that was published in this paper is 2 of the 3 studies are fraudulent. And overall, that paper has been retracted. The authors had actually, some of the authors themselves had tried to replicate it and couldn't. So they'd already lost faith in that finding. But now it turns out it's worse than that. It was probably fraud. So we're going to be talking a lot this week and next week about not so much detecting fraud, because that can be really hard to detect. If the fraudsters are good, it's not really the job of peer review or scientists or evaluators to be able to detect that. We kind of rely on bigger systems like university investigations or journal investigations to detect fraud. But some of these things we can detect ourselves. And in fact, a lot of the blogs and social media that's kind of picking apart research, it's not so much picking apart identifying fraud. That's a rare case. The more common case of what we see on blogs and in social media discussions about the quality of research is stuff that we can all learn to look for and be skeptical of and kind of calibrate our confidence in findings. So that's what we're going to be working on this week. So to start off with, there's this website where we can practice our skills before we go into any of the stuff that I'm going to talk about these next few weeks. We're going to practice, let me make sure the recording is going to capture the whole website. We're going to practice how good we are at detecting what findings are credible or not. And again, here I'm not talking about fraud. I'm just talking about whether a finding replicates, which just means, like, if you run the study again and collect data as close to the original study as possible, do you get the same effect? And for a finding to be replicable, it has to be statistically true. It doesn't have to be true in the broader sense. So I could run a bad study with bad measures and get an effect, and then someone else runs the same study with the same bad measures and they get the same effect. It's replicable, but we're actually not measuring what we think we're measuring, right? So replicable is a really low bar, actually. It's just saying that it's not statistical noise. There's a statistical signal there. If I do the same procedures again, I will get that signal again most of the time. So we're going to take this little quiz. It'll just take a few minutes. And so they define replication as whether a new study detected a statistically significant effect in the same direction as the original study using the same test. So it doesn't have to be as big of an effect as the original, just statistically significant in the same direction. And the replication sample sizes were often, so the number of participants in the studies was often a lot bigger than the original study, 90% power, which means much bigger usually than the original study. So it's very unlikely that if there is an effect there, they probably won't miss it. We'll talk more about statistical power later today. So the experiments they're going to quiz us about weren't picked to be especially good or bad. And the fraction of experiments that replicated was between 35 and 65%. Okay, so we're going to try it as a class. So the first study they're asking us about is whether students who spend 10 minutes immediately before a high pressure math test, writing down how they feel about the test, improve their performance relative to those who sit quietly. So I'm going to ask you, you're going to have to vote, and we're not going to do not sure. We're just going to do yes or no. So the question is, did the replication find a statistically significant effect in the same direction as the original result? So it's the base rate is about 50-50, right? They told us between 35 and 65%. So take a second to think which way you're going to vote. I'm going to ask you to raise your hand. I'll go with the majority for the class, and we'll see how we do as a class over these 10 or 15 questions. Okay, ready? You have to vote yes or no. So who thinks yes, it will replicate? 1, 2. Who thinks no? Okay, not everybody voted, but there's still a clear majority for no, so we'll go with no. That's right, results didn't replicate, and then it gives us more details. So this was the replication study found an effect very close to 0, not statistically significant. Okay, next one. Reading a literary fiction short story improves one's ability immediately afterwards to assess how people are really feeling based on a photo of their facial expression. So the idea is that if you read about fiction, then you can tell what you're better at reading other people's minds, not in the like weird way, but just like being able to tell what people are feeling from their face. So you have to vote yes or no. Do you think that a replication was successful? Do you think this effect replicates, that reading fiction makes you better at judging other people's feelings from their facial expression? Okay, you have to vote. Who votes no? A lot of no's. Anybody vote yes? A couple, yeah, 3, 4, 5. Okay, majority is no. That's right, did not replicate. Okay, let's do the next one. When holding and writing on a heavier clipboard, people assessing job applicants rated them as better overall and more seriously interested in the position. So the idea here is that physical weight gives us a sense of psychological weight. So if we're holding something heavy, we rate the thing that we're judging, in this case, a job applicant, as more serious, heavier, more serious contender than if we're holding something light. This is like the idea of embodied cognition, that our physical experiences affect our cognitive experiences. Okay, you have to vote yes or no. So who thinks yes, it does replicate? Few people. Who thinks no? It's closer this time, but still more no's. That's right, didn't replicate, so we've got a string of no's so far. I think they randomly sample from their set, so it doesn't mean anything about what the next one will be. Okay, this experiment sets up a cooperation game in which participants can produce wealth for one another by trusting the players next to them in the game to reciprocate. So the players begin with an unequal distribution of wealth. When the wealth of other players is made visible, this leads inequality in the game to rise even more over time than when it's invisible. So the idea is if you have to play a trust game where everyone can get better off if they cooperate, if you make the discrepancies in wealth visible, people actually cooperate less and the inequalities get worse. But if the discrepancies in wealth are invisible, then people cooperate more and there's more equality at the end of the game. Okay, so yes or no, does this replicate? Who votes yes? Quite a few yeses. Who votes no? Just a few no's, so we'll go with yes. That's right. All right, we're doing really well as a class so far. It's a pretty big effect. So the effect size is about half a standard deviation. Although you can see from this confidence interval, even the replication study that had a lot of participants still isn't quite precise about how big the effect is. Okay, next one. Hand washing reduces how strongly people feel the need to justify a choice they made a few minutes before. So you make a choice, maybe it's morally ambiguous choice. You either wash your hands and then you feel less need to justify it, or you don't wash your hands and you feel like you need to justify it. Have you guys heard of this finding before? Some of you have? Okay. Has anyone taken this quiz before? Okay. All right, so who votes yes, this replicates? Oh, quite a few people. Who votes no? Okay, there were more yeses than no's. Nope, it did not replicate. So it's interesting that you seem to recognize this finding but it turns out, and I wouldn't be surprised if there's a correlation there, right? The more you've heard of a finding, maybe the less likely it is to replicate, because the things that make the news are the most outrageous things. I don't know, that's a hypothesis. Okay, the likelihood of choosing a charity is higher when potential donors know that the overhead for that charity is already covered, compared to when the donors have to pay that overhead themselves. So do you think that people will donate more when they know that the overhead is already covered, rather than when they, like when you're donating to a charity, it says, you know, you're donating $50, but 5 of it will go to overhead or something like that. Okay, will this replicate? Who thinks yes? Who thinks no? A lot of you didn't vote, that there were a few more yeses. Let's try again. Okay, you have to pick yes or no. Who thinks yes? Who thinks no? Okay, more yeses than no's. That's right. All right, so far we've only gotten one wrong as a class. I think there's just a few more. Priming analytic thinking, so thinking analytically, by getting people to look at a photo of the thinker, makes people report less religious belief. So if you show people a photo of the thinker, the statue, they report being less religious. Does this replicate? Who thinks yes? Who thinks no? Okay. Maybe you've heard of this one too. I don't know. It did not replicate. This is an interesting case where the original authors, so when it failed to replicate, the original authors completely accepted that result and said, yep, you shouldn't believe our original study anymore, which is actually pretty rare. Okay, and then imagining eating M&Ms 30 times makes people eat fewer M&Ms when you offer them M&Ms immediately after. So in one condition, you ask people to imagine eating M&Ms and do that 30 times. Another condition, you don't ask them to do that. Then you give people M&Ms and you see how many they eat. Do you think people will eat fewer M&Ms in the first condition where they spent quite a few minutes imagining eating M&Ms? So do we think this will replicate? Actually, don't remember the answer to this one. Who thinks it replicates? Yes? Who thinks no? Pretty even. I'm going to go with no. I think there were more no's. Oh, it did replicate. So it turns out, if the interpretation of the study is correct, then it's true that imagining eating M&Ms means you eat less. But remember, replicability is a low bar. It doesn't mean the interpretation is true. It just means if we did the study again, we would get that result. What it means is a whole nother question. All right. People can tell how tennis players feel during high intensity game moments without seeing their face, just by looking at their body. So do you think you can tell? I think what they mean by can tell how they feel is like whether they're feeling positive or negative, probably, maybe not much more fine grained than that. What do you think? Who thinks yes, this is replicable? Okay, who thinks no? Pretty close, but I think there were more yeses. Okay, it did replicate. When women are told they will be given preferential treatment in a competition, that their scores will be artificially boosted, more women choose to join the competition. Okay, so is it replicable? So again, it doesn't mean it's true in a broader sense, but if we do the exact same study over again, will women in the study choose to join the competition more if they're told that their scores will be artificially boosted? All right, who thinks yes, this is replicable? Not many people. Who thinks no? Okay. Nope, this did replicate. I didn't know about that one either. Okay, let's stop there. But if you want, you can go to the website and you can keep going and test yourself more. Let's see how we did. So our score was about the same as the average individual taking the quiz. Scientists did slightly better. This is if you average everyone who's taken the quiz, which is thousands and thousands of people, they do about the same, maybe a little better than scientists. And this is when people bet money on the outcomes. So it turns out this has been shown a couple times actually, that if you ask just people who take this quiz just because they're interested, so they might not be experts, but they at least have some interest in this, whether you tell them they're betting money and they actually can win money on their bets or not, they do approximately about equally well if you average everyone. So that's what these two bars show, that introducing money into it, making it a bet, doesn't really change the accuracy of how people do. And people tend to do as a group, if you average everyone, people who are not experts do about as well as experts. Scientists surveyed about this, which is a little bit worrisome. Okay, so what we're going to be talking about today is what we can look at to evaluate a study and maybe get better at predicting it. But honestly, I think predicting replicability is not that important of a skill. What you really want to do is predict the more general validity of research. So one of the reasons you might be skeptical of a study is that you think it won't replicate, but that's not the only reason. Something could be replicable, but not true or not useful for your purposes. So, okay. So today we're going to be talking about the 4 validities. This is one way of breaking up the validity of research. I'm not saying this is the way. There are a lot of different kind of models, and psychologists tend to adopt this way of breaking down validity, but people in different fields will break it down in different ways and will call it different things. So it's kind of confusing. I'm going to go with this language for today, and that's what you'll find in most psychology literature. So construct validity is, are you measuring what you think you're measuring? It also applies to manipulation. So if you have a manipulated variable in your study, construct validity could apply to, like, are you manipulating what you think you're manipulating? So it's the validity of how you operationalize your constructs. We're not going to talk about that as much today because we've talked about it in designing surveys. That has a lot to do with construct validity in the context of surveys. So how do you know that you're measuring what you want to measure, that your measure is valid? What we call internal validity is, are your causal claims valid? So it's the validity of inferences about something causing something else. And we'll talk about that quite a bit today. External validity is, are any claims you're making about how your findings generalize valid? So generalizing to other populations or generalizing to other contexts. And we'll talk about that a bit. And then statistical validity, which has to do with replicability, but also there can be other kinds of threats to statistical validity besides just not being replicable. But it's, you know, things like, are you confusing noise for signal? Are you missing an effect that's there, or seeing something that's not there? Are your statistics correct and valid? Okay, so just thinking about these types of validities, I want to stop for a second and ask you all what you think about which type of validity do you think is most important? Which type of validity do you think might be the hardest to achieve or the easiest to achieve? And there's no right or wrong answer about these. There's a lot of debate about which validity is most important, but they're pretty much all really important. So it's really hard to say, right? It's really hard to rank. It's like asking which of your kids is your favorite. You can't really rank them, or you're not supposed to anyway. But people have opinions, and I'm curious if you all have any opinions about which is most important or which might be the hardest to achieve or the easiest to achieve. What do you all think? Yeah.
I feel like with psychology a lot of the time, like statistical validity is really hard to achieve. Like just like read, like if you're going to study again, like reaching that again is hard. And I feel like a lot of factors are hard to control. So it's like, even if you do have something that's statistically valid, like, is it really?
Yeah. Yeah. So statistical validity, I think it has many components that makes it hard. It's also quite technical. Like you need to understand a lot of technical stuff to get it right. Yeah. So it could arguably be considered the most difficult. Yeah.
I think external validity is pretty hard because if you measure something with a specific population and you claim that it's the same everywhere, it doesn't make much sense because cultures are different.
Yeah. Yeah, and that's just one aspect of external validity. So to have external validity, you need to make sure that if you're generalizing to a broader population than what you studied, that you have the evidence to do so. So if you have a convenience sample of an online panel that's not representative of anything, it's really hard to know who you can generalize to, even within that. Like, let's say it's Australians. If you don't have a representative sample of Australians, it's not even clear that you can generalize to Australians, much less to people from other cultures and so on. External validity is interesting because it's one of those where it's pretty clear what you would need to do to get there. So to be able to generalize, you need to sample from the things you want to generalize to. If you want to generalize to other people, you need to sample other people. If you want to generalize from the lab to the real world, you need to sample from the real world. You need to go and do the study in the real world. If you want to generalize from one way to manipulate anger to a different way to manipulate anger, say that it's not just about this one way to manipulate it. I think it's true of anger in general. If I make people angry, it's going to have this effect. Then I need to sample from different ways to manipulate anger. If I sample a lot of different ways to manipulate anger, and I show the effect on my outcome variable, whichever way I manipulate anger, let's say I think that anger makes people buy more or something like that, then I can generalize to say it's not just this manipulation that made people buy more, it's this construct of making people angry. That touches on both construct validity, but also external validity, because what I'm doing is I'm generalizing from my one way of studying this to it would work even with other ways of studying this. And so for all of those kinds of external validity, all you need to do to get external validity is actually sample those things and show that the effect holds when you sample different people, different ways of studying the thing, different contexts. But that's really, really hard, right? It's often maybe even impossible to go out and sample people from a completely different part of the world or a different population, or to use other measures, or to do something outside of the lab, or in the right context. So sometimes external validity is literally impossible if you don't have access to the things you need to sample. But in some ways it's easier because you know what you would need to do, right? At least there's a clear way, whereas some of these other validities, it can be really unclear how you could ever achieve them. Any other thoughts on which ones? Yeah. Either.
I was just gonna say constructibility, I would say is the important because everything on both parts is not making them.
Yeah. Yeah. So a lot of, I think most people who are experts in this and in research methods and psychometrics would argue that construct validity is the most central. Of course, they are people who specialize in construct validity, right? Psychometricians are all about developing good measures. So they're a little bit biased in my opinion. But it is a common view that if you're not measuring what you think you're measuring or manipulating what you think you're manipulating, then nothing else matters. You could say that of all of these though. If what you're measuring is actually statistical noise and you think it's a signal, then nothing else, it doesn't matter whether you're measuring what you think you're measuring. So all of them kind of don't matter if you don't have the others. But there are a lot of people who see construct validity as the most fundamental, that and you could see it as a precursor, right? You shouldn't even be running your study until you validated your measures or your manipulations, right? Especially if it's going to be a really important study, a study that you're investing a lot in, that people are going to take and build a lot off of, then probably you should, before you do anything else, make sure that you know how to measure and manipulate the constructs you want to measure and manipulate, and that you can do that independently before you do the study. It's pretty rare though. So there's more and more meta research, that's research about research, showing that it's actually quite rare for people to use validated measures. They very often just come up with the measure on the fly as they're doing their study, at least in psychology.
I was just gonna say, I feel like, because you can do manipulation checks and things like that, especially with psychology, but yeah, you don't see it very often.
No, yeah. So we've done, and other people have done research, actually it was an honors thesis in my lab last year, where we just took a sample of articles published in social and personality psychology and looked at how often they used measures that had been previously validated versus they created their own. Like we wrote 3 items to measure this thing, and it's really common to use. They're called ad hoc measures. It's really common practice. And even when the measures are validated, the validation is not great. And there's a lot of interesting literature. There's a paper by philosophers, actually, but philosophers of social science, called "Is Construct Validation Valid?" where they argue that the common way that we do construct validation, when you design a survey, you validate it and so on, it's just kind of going through the motions and checking boxes, but you're not actually thinking very deeply about what you're trying to measure and whether you're measuring it. It's a really interesting, short, pretty accessible paper. Another great paper I like about construct validity is a paper critiquing. So there were a bunch of surveys designed about internet addiction, like Facebook and social media addiction. And it became this like really popular topic, and in parenting blogs and things like that too, people got really worked up about the idea of social media addiction. And so some researchers who I thought that this was really clever, what they did is they took the items on these Facebook addiction questionnaires and just changed the part that's about online friends, social media friends, to offline friends, like just regular friends in real life. And so the questions were like, sometimes even when I'm not with my friends, I think about them. Or like sometimes when I start hanging out with my friends, I end up hanging out much longer than I intended to. Or like a day that I don't see my friends is a bad day, things like that. That's what, like those kinds of items were on the addiction measures. And they showed that you just ask that about anything else that people like to do, like hanging out with their friends, and like 40 or 60% of people are addicted to their real life friends. So there's a critique of these online addiction measures, where those online addiction measures probably passed many of the quantitative tests of validity. Like you have to show that it has a good factor structure, that it's reliable, that it correlates with what it should correlate with, that it's stable over time. All these steps of survey validation, they probably pass those tests, but it's just like a common sense thing to ask, is it right to put the label addiction on this? Like if people endorse these items about almost anything else, you wouldn't necessarily call it an addiction. And that can't be answered quantitatively. And so I think construct validity is really, really tough because it can't be reduced to a number. People try to, it's a very common practice to try to reduce it to a number, but you can't take out the critical thinking. And actually, that's true of all of these validities, even statistical validity, which has the most to do with numbers. In the end, all of these are judgment calls. And there's not a single number you can put on these things to say it has this much validity. That's what I think makes research methods really exciting, is that you can't reduce it to a number. And I think it's one of the last things that AI is going to be able to replace humans for. So like, yeah, AI is going to be able to do a lot of things about research design. If you tell it what you want to study, it's going to help you come up with a better design and so on. But evaluating research and asking really deeply, like, is this actually doing what it says it's doing? Is this conclusion correct? Is it warranted given the evidence, that's going to be very hard for it's hard for humans to do too. So it's going to be hard for AI for the same reasons it's hard for humans, but I think it's an exciting place where we can really add value. Okay, so construct validity, yeah, it's really tough. It's often ignored. It's interesting. So one of the things, another honors project in my lab was looking at social and personality psychology papers and what limitations authors say there are in their papers. And we categorize them into these 4 validities. And we were very curious to see what authors say was a limitation in their paper, because if our impression of the literature was that construct validity should be coming up a lot. It's just so hard to get right. People don't spend a lot of time on it, et cetera. But it actually didn't come up that much. The one that came up the most is external validity, because it's so easy to say, oh, we don't know if this would generalize to other populations or other contexts or things like that, right? That's a kind of a throwaway limitation. No one's really going to hold it against you. And so you can easily admit that.
Is internal validity kind of easy to get away with that wording?
So internal validity, we're going to talk about that a little bit. So it's the idea that you should be very careful if you're making causal claims that you have good evidence for those causal claims. And so what that often comes down to in psychology, and now we're anticipating the lecture, but this is good, I'll be able to skip some of what I'm going to talk about later, is that if you're doing an experiment and you're manipulating the independent variable, the predictor variable, rather than measuring it, then you're on more solid ground to say that any effect of the independent variable and the dependent variable is a causal effect. There's still some threats there that we'll talk about. But if you're not manipulating, if you just measure 2 variables, you find an association, and then you say that one is causing the other, then you're on shaky ground. And so what we found in authors' limitations is that if they didn't manipulate, they didn't do an experiment, so they just measured all their variables, it's called an observational study or a correlational study, or I think you talked about earlier, all the different words this stuff goes by. Then you probably shouldn't make a strong causal claim, or if you do, you need to be really upfront that you're making a lot of assumptions there. And you have to talk about what the alternative explanations might be and so on. And authors rarely do that. What we do see in limitations is say, because this was an observational study, we shouldn't make any causal inferences. And they'll do that in the limitations section, and the title and abstract will have causal claims. And so we'll talk about an example of that too. So all of these validities are hard. We give a lot more attention to some than others. So in psychology, we give a lot of lip service to external validity. We talk a lot about, we kind of beat ourselves up for not having representative samples, et cetera. We still don't do the work of actually getting external validity, but at least we're more upfront about it. According to our analyses, people say that as a limitation, not so much the other 3. With internal validity, they'll often say that it's a limitation and then ignore that fact in the rest of their paper. They'll go on and make causal claims without justifying them anyway. So we're going to organize the lecture into a couple of different parts. Why is that not showing? There we go. So we're going to be talking most of the lecture about testing for differences and the 2 different ways of testing between existing groups versus manipulated groups, where internal validity is very important. If you're making claims about differences between groups, or these are usually causal claims when you're testing for differences. So you need to be really careful about internal validity. And then we're going to talk about different kind of research, which is generalizing to a population where you're estimating frequencies. You want to know how many people experience mental illness in their lifetime, or how many people buy a new car every year, or something like that. You want to know the levels of a variable in populations is 1 variable. Here, you're usually interested in at least 2 variables. And here, external validity is more important. So I'm going to keep coming back to those themes. Okay, so talking about these 2 ways of testing for differences. One is existing groups, so comparing existing groups. So where your X variable, you might have group 1, group 2, et cetera, on the X variable, and you're interested in how they're different on the Y variable, but you measure both X and Y, and you can conclude that the variable X is or is not associated with variable Y. So for example, you might be interested in how different genders differ on risk taking or anxiety or whatever, how different years in school, maybe year 9 versus year 12 differ on different things, how what state people are from might be associated with different things, their age might be associated with different things. There's many examples you could think of research like this, where you're interested in different groups and their levels on different variables. The other way to do it would be manipulated groups. So you have different levels of X that you randomly assign people to, and then you measure their levels of Y and look at differences. So for example, you could randomly assign people to what kind of social context they're going to be in. Are they going to come to the study and do it alone, or are they going to do it in a group? And does that affect their answers on your outcome variables, your dependent variables? So this would be an experiment, right? If you manipulate the X variable and you randomly assign people to different levels of the X variable, that's an experiment. And so which one of these you do has implications for what kinds of internal validity threats you need to worry about, what kinds of threats to causal inference you need to worry about. So in general, if for causal inference, for internal validity, manipulated groups are better than existing groups. But there's a reason why we don't always just do experiments and manipulate our X variable. One thing is that some things can't be manipulated. You can't randomly assign people to be different ages or to live in different states or to be different genders. So other things can be manipulated by modifying conditions, but you have to modify conditions so much that we can't generalize to situations we want to generalize to. So maybe I could manipulate people into different levels of income or wealth or something like that by giving some people a lot of money. But that's a very different kind of experience, even if I had the money to do it, than kind of having that wealth through the means that people otherwise come into wealth or money. So it might not be the same to randomly assign people to have more money or less money, might not be psychologically the same as the natural variation, how much money people have in the real world. And you could think of a lot of variables like that, where sure, we could kind of recreate artificial levels of that variable and randomly assign people to them, but is that the same psychological variable as the natural variation in that variable? Other reasons we might not do an experiment is that sometimes we have an interest in a particular outcome and we want to understand that outcome. For example, depression or professional success or creativity, and we want to know its causes. So if we don't have a particular cause in mind that we want to test, we want to kind of just do a lot of exploratory research on the potential causes of that outcome, then we're probably going to start by measuring all the potential causes and seeing which ones are associated with the outcome as a starting point for coming up with causal theories about what might be causing the outcome. Experiments are good for getting at descriptive causation, but not very good for getting explanatory causation. We won't go into that very much, but the idea is that if you do an experiment and you do it well, you have good construct validity, good control and everything else, you might learn that variations in X cause variations in Y, but you won't necessarily learn why. What is it about X or what is it about my manipulation that caused it? Waiting on an experiment can mean delaying evidence-based solutions. So sometimes we have evidence from measured variables, we have correlational evidence. We could do an experiment, but we need an answer now. And so we're going to base our answer on the correlational evidence. So it's another reason why it's good to get good training in how to make causal inferences without an experiment. And experiments favor things like light touch interventions like nudging. It's much easier to do an experiment on what happens if I just change the order of the questions, or what happens if I move the healthier food to, closer to people rather than further away, things like that, than it is to experiment on structural changes. Like what if I completely change the food that's available in the cafeteria? Or what if I, give people intensive training on healthy habits or something like that? So by prioritizing experiments, we might be like looking where the light is, right? Looking under the lamppost, that kind of metaphor. We're going to do the easy stuff, that stuff that's easy to manipulate, and we might ignore harder things that maybe can't be experimented on. But if we valued correlational research, we would see some really big associations at the structural level that could point to some more important causal effects. Also, there's the fact that people who are willing to be experimented on and randomized into conditions may be unrepresentative. So if you think about medical trials here, right? Like people who sign up for medical trials, and then we generalize from them to whether the drug works in general. But if people who are willing to sign up for a medical trial and take a chance of being on a placebo and not know, or take a chance to be given a drug who we don't know if it works yet, those people might be quite different. And for example, maybe they're much more motivated to adhere to the treatment that they're given. And so if that's the case, then the treatment might work for those people, but it might not work when we scale it up to everybody, including people who are not nearly as motivated as those participants. Similarly, knowing that you're part of an experiment may alter the results. One of my favorite experiments to teach about, which I really puzzle over the interpretation, was from the guys who did Freakonomics. So they recruited people who were considering making a major life change, like quitting their job, quitting their relationship, moving, etc. And they asked them, would you be willing to be randomized to whether to make the change or not? And so they got, I think, tens or hundreds of thousands of people to sign up on their website to be randomized into making a life change or not. And they found that on average, people who made the change were better off later on than not. It's a really fascinating experiment, but you have to wonder, first of all, those people probably aren't representative. Second of all, knowing that you're doing it for science might alleviate any of the negative side effects of having made a big change. So maybe you have some regrets about changing your job or moving or whatever, but you don't fully own the decision in the same way that if you weren't in the study, you would maybe blame yourself more for having done that, and maybe the negative aspects of it would weigh on you more. Anyway, it's hard to know, but there's a lot of difficulties in interpreting experiments and all kinds of studies, right? Many of these concerns apply to all kinds of studies. So this kind of manipulation experiment is also known very often in the outside of the scientific world as A/B testing. So you might have heard of that. And there's this article from Wired from a while ago, and this slide is from my colleague Oleg Orminsky from University of Chicago, where I think this was supposed to, sorry, one second. You can't see what's behind the text block. Let me fix that. Okay, so this was used in the Obama campaign, and the Wired article talks about the guy who kind of heard Obama speak at Google and thought Obama had a really experimental mindset and wanted to work for his campaign. So this researcher from Google kind of quit his job, went to work for the Obama campaign, and introduced the idea of A/B testing. This was back in 2008, the first time Obama ran for president. And there were a couple of things he suggested trying out. So trying different pictures, trying different wording on their sign-up pages was to get people to sign up as volunteers or donors to the campaign. And this was a relatively new idea for political campaigns back then. And the group had really strong ideas about what would work better, but they agreed to submit it to testing. So they just did different versions of the website, randomly assigned people traffic to the website to different images and different wording. And what they found was that the learn more, or I can't remember which one it was, I think it was learn more that worked the best, and that this black and white photo worked much better than the blue photo. And in the Wired article, they talk about how this was shocking to Obama's team, that it was really inconsistent with their instincts. So almost unanimously, staffers expected that a video of Obama speaking at a rally would handily outperform any still photo, but in fact, the video fared 30% worse than even the turquoise image, which was not the best image. So had the team listened to their instincts, if they had kept the sign up as a button text and swapped out the photo for the video, the sign up rate would have slipped to 70% of the baseline. So this is, the idea that we might have strong assumptions or instincts about what works, but in many areas, those might not be very valid. Now, that might not generalize, right? There are probably many areas where instincts or assumptions are pretty good, but in this case, it wasn't. So this Wired article goes on to talk about some of the pros and cons of A/B testing. And so they give an example at a gaming network where executives found that crisp, clear prose was outperforming hyped up buzzwords. But in previous years, the opposite had been true. Why? They talked and talked about it, but no one could figure it out. Soon they realized that it didn't matter. A/B would guide them at the ground level, so there was no need to worry about why users behaved in one way or another. This is kind of a risky road to go down, to just follow the data without understanding or even having a theory about why it's going that way. So I think this kind of points to the importance of human judgment to still come in there and at least track what's going on and not just be a slave completely to the data. But this was back in 2012. It was saying one of the trends in A/B testing is to automate everything and let the data basically decide. No human oversight necessary. But they also talk about some of the downsides of this approach. They said testing tools, A/B testing, can really motivate the engineering team, but they can also wind up giving them huge incentive to try only small changes. So it's a lot easier to do A/B testing on like the word and on the button or things like that. And then they have this quote from Henry Ford: "If I'd asked my customers what they wanted, they'd have said a faster horse. If you rely too much on the data, you never branch out. You just keep making better buggy whips, right? So you never think outside the box and just do something completely different." So we have to think about the power of experimentation. It's very powerful. It can be really useful. It also has its limits, and so there is still room for human thought, human creativity, human innovation. Okay, so we're going to talk a bit more in depth about internal validity. So when we're talking about differences between existing groups, we haven't manipulated anything, then it's very difficult to establish causality. It's not impossible. It can be done. So for a classic example you hear in philosophy of science is that the idea that smoking causes cancer was not discovered through experimentation. They didn't randomly assign people to smoke. It was through a lot of measurement of a lot of different variables, ruling out different possible mechanisms, and eventually coming to the conclusion that smoking causes cancer. But you have to consider all the possible threats, and they're very many and very serious. And it's often hard to think about, to imagine all of the different possible threats to your causal interpretation, all the different possible alternative explanations. So one is just reverse causality. Is it plausible that it's not X that causes Y, but actually Y that causes X? So if you observe, for example, that people living in Victoria versus New South Wales have different preferences for weather, maybe people in New South Wales care about the weather a lot more, people in Victoria are more fine with different kinds of weather. Is it the case that it's living in those states that causes their preference for weather, or could it be that the preference for weather causes people to live in different states? Now, how plausible that is would depend on data on mobility. How often do people move? Do people tend to stay in the same state? If people are not moving much, then it becomes less plausible that their preference for weather is driving them to go live in another state. But in some cases, Y causing X might be plausible. And again, here, this can't be reduced to a number. You have to think about, does this make sense in this particular case? And then the other kind of threat, which is very, very broad and can take many different forms, is the idea that a third variable is causing both X and Y. And so it's making it look like there's a causal effect between X and Y, but actually it's this third variable. So for an example of that, I'm going to come back to an example you used earlier this semester. So you talked about, I think, based on the slides, you talked about this study about how people who occasionally drink alcohol have lower depression risk than people who never drink alcohol, right? So this is an association between existing groups, comparing people who drink a little bit to people who never drink, and finding that people who never drink are actually worse off in many ways, specifically risk of depression. Did you already talk about possible third variables here? Do you remember any of those? No, can you think of any? So one hypothesis is that not drinking causes depression. Another hypothesis is that depression causes not drinking, right? That would be the reverse causality. What would be a third variable hypothesis, something that could cause both? Yeah.
Maybe occasional drinking is linked to socializing.
Yeah, so maybe socializing is the third variable here. So socializing causes occasional drinking. If you go out more, you're going to drink more once in a while. And not socializing causes less drinking or not drinking at all. And also socializing causes less depression. So if that were the case, if socializing causes some drinking rather than none, and if socializing causes less depression, then you would get an association between not drinking at all and being more depressed. Yeah, that's a great example. Any other examples? Yeah. Yeah. Yeah, so that's great. So maybe having a personality type that's all or nothing would lead people to not drink at all or drink a ton, but compared to drinking a little bit, it would lead people to not drink at all. And it might also mean that they do other things in an all or nothing way, and maybe that causes depression. Yeah. Yeah, so there are probably hundreds of variables that could be a third variable explanation here. And so imagine that you're these researchers and you want to rule those out. So, okay, we can measure socializing, we can measure personality, you know, whether you have an all or nothing mentality. But then we have to think about, what about physical disability? Maybe if you're on some other drugs to treat a physical disability, you can't drink because that's counterindicated for your prescription. But also that could cause depression, right? We could come up with tons and tons of them. And in order to ever be confident about our causal explanation, let's say we think that it's not drinking causes depression, we'd have to rule out or have pretty good evidence that it's not all of those other things. And so it's really, really difficult. Not impossible. Again, there are cases when a lot was at stake, where researchers really invested enough. I mean, climate change is another example, right? Where we can't manipulate things. We have to really do a lot of research, collecting data on a lot of variables to figure out the causal effect of human factors on global warming, for example. Okay, so someone asked earlier, like in studies where they don't do experiments, do they still make causal claims like with vague language? And that's definitely an issue. And there's a lot of debate about what language is justified when you can't make a strong causal claim. What are you allowed to say? So you're allowed to say X is associated with Y, or there's a relationship between X and Y. You're not allowed to say, we know that X causes Y. You can say, my theory is that X causes Y. My study can't determine that. But there's many, many other verbs. Oops. There's many other verbs that, what is happening? Okay, that people use, and here are different fields. What? I can't even select it. Does anyone know how to work? It's not, it's in math form. Oh, there we go. Okay. Okay. Go back. So different fields have different norms about what verbs are allowed. So for example, some fields say predicts is a causal verb. If you say X predicts Y, in psychology, we tend to say no, X predicts is not causal, where it's okay to use it even when you don't have evidence of causal. And it also depends how you're using these words. So the same phrase might be causal in one sentence, but not causal in another, depending on how you're using them. So if you say when X goes up, Y goes down, that could be descriptive, but you could also phrase it in a way that it sounds like you're saying that X going up makes Y go down. So there's, again, no hard and fast rules, and you just have to use your judgment in the given context of your own research or the research that you're evaluating. So a quote that I like is, correlation doesn't imply causation. We all learned that, in first year university. But he says, but it does waggle its eyebrows suggestively and gesture furtively while mouthing, look over there, right? So correlation is not irrelevant to causation. If you find a correlation between two things, the probability that there's a causal effect should go up a little bit in your mind, but that's very, very far from knowing that there's a causal effect. So I'm going to pick on some friends of mine who had a paper where they did a pretty good job in some places of being careful about causal claims, but not consistently. And again, this is very common, right? Researchers will say in one place we can't make a causal inference, another place they'll go and make a causal inference. So this paper was about looking at differences over the life course. So they had longitudinal data on people over decades, looking at marital histories, so getting married, getting divorced, getting married and staying married, never getting married, and their links with subjective well-being, happiness. So what they say they found is that they found that the consistently married people, so people who got married and didn't get divorced, had higher life satisfaction, subjective well-being, happiness, compared to the consistently single, so the never married, and the varied history, which is sometimes married, but then not married again, and then married. But the two latter groups didn't differ from each other. Okay, so that's very descriptive, very association talk. They're not saying anything causes anything. They're just describing this group is higher than that group on happiness. But then and they actually even acknowledge in the discussion section that there are a variety of explanations for these results. Marriage may indeed lead to higher satisfaction, so X causes Y. That's one possibility. Or those who don't have the consistently married trajectory might experience social isolation or additional stress, or these groups may differ from each other before these transitions even begin. So they're talking about reverse causality. Actually, that's not reverse causality exactly, but it could be, right? It could be that being unhappy causes you to not get married or to get divorced. Or the groups may have other differences as third variable, but they don't specify third variables. So they're pretty careful about it, but in the abstract, they said that their goal was to determine if different marital histories have unique impacts on well-being later in life. So impacts on, to me, is very causal, and we could debate that. Maybe the authors could argue that it's not, but actually I asked them what they think since I'm friends with them, and they admitted that in retrospect, they probably shouldn't have used this language in the abstract. Now, again, they can have the theory that it is their marital trajectory causing happiness, but then they should say that it's coming from their theory, not from the data. The data are completely consistent with all of the causal explanations. So then you have to use judgment, you have to use evidence from outside of the study, et cetera, to make the case, if you want to make the case that it's X causing Y. Okay, I've peppered some quiz questions in throughout my lecture to help you guys kind of give you an idea of the kinds of things I'm hoping you're getting from this lecture. So here's the first one. You can just jot it down for yourself. I'm not actually going to ask you to answer. Which of the following is true about finding differences among existing groups? And the correct answer here would be C. It's possible that X causes Y. Maybe the probability, our subjective probability should go up a bit, but I wouldn't say that it's very likely, not without much more information about other data, other theoretical reasons, et cetera. Okay, so that's differences between existing groups. What if you manipulated your X variable? What if you did an experiment? So cause and effect relationship can be established much more easily in this case, but there's still some possible threats and they should still be taken seriously. And we're actually going to spend quite a bit of time on this because I think it gets overlooked, but I don't want you to forget that actually causal inference internal validity is much harder in this case than this case, but we're still going to spend quite a bit of time talking about threats to causal inference in experiments because people tend to assume, oh, experiment, therefore causal inference is fine. And that's not true. So one important possible threat that we're not going to talk a lot about, but just a little bit, is the idea of confounds. So even if you manipulated X, your manipulation might have inadvertently also manipulated other things. And it's very, very hard to know for sure that you didn't accidentally let something co-vary with your manipulation. So one example is when Google was doing A/B testing, one of the things they were trying to test was this was early on in Google, when you do a search, the number of search results it shows per page. So the default was 10 at the time, it actually still is, so you know how this test worked out. But they tried 10, 20, 25, and 30. So users would go to Google, type something in the search, and they would get randomly assigned to a condition of seeing either 10 results on a page or more. And what they found was that 10 was way better. People, quit, left Google, et cetera, much more if they were in one of the other conditions. But what happened was there was a glitch in the experiment. They called it a disaster, which was that the groups that were assigned to see 20, 25, or 30 search results, those pages loaded much slower than the page that was only showing 10, which in retrospect, obviously, if they hadn't done something to compensate for that, that would be a confound, but they didn't think of it, and they may never have discovered it. They may have thought that was really just how big of a difference there was between 10 versus 20 or 30 search results if they hadn't gone and checked that there wasn't this confound. So that's, it's the same idea as a third variable, right? It's a third variable in a case where you think you've isolated all the third variables. You think that by randomly assigning people to your manipulated conditions, that you've removed all the third variables, and you have mostly, you've done a really good job. It's much better than studying existing groups, but it's still possible that something is co-varying with your manipulation if you're not careful. Okay, so that's one threat. The other one that we're going to talk more about is the idea that participants or respondents might drop out in non-random ways. If participants drop out of your study between starting the study and finishing it in non-random ways, it's called selective attrition. And it turns out that's a really big threat to causal inference, and one that's mostly ignored by psychology researchers. Okay, so I'm going to go through a paper by Zhu and Fish back from 2016 and just highlight the key points, but I really got all of this from their work. It was really, really important paper. So they started talking about how when they went and read the literature, similar to the honors project that I talked about, where we go and look at, for example, limitations or whatever, they went and systematically looked at 1 or 2 years of psychology papers in 2014 and 15. And they found that most published research in psychology doesn't report how many participants dropped out of the study. So they'll say their sample size, but it's unclear if that's the starting sample size or final. It's usually probably the final sample size, because that's the sample size for their analyses. So those people they need to have reported everything that's in all the variables that are in the analyses. And what they found was that actually probably many researchers don't know how many people are dropping out, especially now that most research is online. So they talk about how many survey software, a lot of the different survey softwares actually won't tell you if someone started the study but didn't finish it, because if it doesn't record the data until the people get to the end, then you wouldn't see the partial data. So one common survey software is Qualtrics. They said that in Qualtrics, it will tell you, but if the person doesn't, the default in Qualtrics is if the person doesn't finish the survey, it takes a week before it uploads the data to your data set. So let's say you run your study in a day and you download the data at that point, you don't do anything outside the default, you would not actually see the people who started the study and didn't finish it. If you go back and download it a week later, you would see it. Or if you close the study before you download it, then it uploads everything and you would see everything. But they concluded, based on what they perceive to be common practices, that most researchers probably don't even know how many people start their study and don't finish it, and certainly aren't reporting it in their papers. So they went and did some studies. They took some paradigms that are very common in social psychology, because they're social psychologists, and they repeated those studies online, and they actually measured how many people drop out. But they were also interested in, was the dropout rate similar for all conditions? So what is the dropout rate, first of all? Is it similar across conditions and experiments? And actually, we need to worry not just if the dropout rate is different in different conditions, even if it's the same, we need to worry about whether people are dropping out for the same reason across all conditions. And spoiler alert, they found that the dropout rate is very high. It's not always similar across conditions, but even when it is, there's very good reason to think people might be dropping out for different reasons across different conditions. And if that's the case, you have to be very worried about your causal inference. So let me give you the results. So this is one table. It's just going to show the dropout rate for 6 different experiments that are using common manipulations used in social psych. And I'll show you the dropout rate for each of 2 conditions in those experiments. So for example, the first one is terror management, which is where you make some people think about their own death and other people think about something else, unpleasant, but not their own death. So the mortality salience condition, they think about their own death. The control condition is thoughts and feelings about physical pain, but not death. They find dropout rate is 30 to 35%. In a study on control levels, so think about something in an abstract way versus a concrete way, dropout rates 44 to 38%. A power study, so recall a past episode where you were in a powerful role or powerless role, very similar dropout rates, but also quite high. Regulatory focus, ego depletion, and elaboration mode. Some dropout rates extremely high. So if you have to write a 100-word paragraph without using letters A or N, more than 3/4 of participants drop out. And in these studies, they paid participants 50 cents for a 5-minute study, which is consistent with the guidelines for academic requesters, which were written by Turkers together with researchers. So these were done on Amazon Mechanical Turk back before. So now I think the data quality is even worse than it was at the time. So they found that on average, dropout rate is about 40% for these kinds of studies where it's a 5-minute study and you probably have to write something but like 100 words at most, right? Often these are not extensive writing tasks. So one of the research questions was, can we reduce dropout rates? Because it's considered, these dropout rates are not considered acceptable. Under 20% may be acceptable, depends on the context. Over 20% and this high, really, really concerning. So they read the literature and came up with some ideas about how you could reduce dropout rate. So there's a couple of things that people had suggested but hadn't tested. So one idea is that you tell people ahead of time they're going to have to do some writing. So anyone who wants to drop out drops out then, and that reduces the problem. So they don't even enter your study. You get a much less representative sample, but at least you don't have to worry about as much about dropout. Another idea was that you make them feel accountable and identifiable. So you ask them for something identifying at the beginning, or you ask them to pledge that they will answer open-ended questions. So it seems to be the point of dropout for a lot of people. And you also emphasize to them that the research is not going to be as valid if they drop out. So what they decided to do was, let's try all of these things at once and see how much we can lower the dropout rate if we do all of these things. So they did a study where at the beginning of the study, they showed the participants in an online panel this paragraph saying this is an anonymous survey consisting of multiple questions. It'll include open-ended questions. Many MTurk workers do not like answering open-ended questions and tend to quit. If a sizable number of people quit, the data quality will suffer. Please make sure you do not mind open-ended questions before taking the survey. Then they were asked to type out, I will answer open-ended questions and give their MTurk ID. And in this condition, compared to the control condition where they didn't do any of this, dropout was 20% compared to 47%. Still pretty high, but this did work to some extent, but it didn't work enough to make it. Yeah, they think that this is still too high. Okay, so let's look at why this is a threat for causal inference. So first, let's take a case where dropout is really different in the two conditions. So if you have to write a 100-word paragraph without using A or N, 75% of people drop out. If you have to write a 100-word paragraph without using X and Y, only 23% of people drop out. So already this is a threat to causal inference because you're getting a lot more people dropping out in one than the other. So there's something else different about the conditions. And you're getting different people staying in, right? If you're getting only the most motivated 22% versus the most motivated 70 whatever percent compared to the most motivated 20-something percent, that's pretty different people. And they also found that actually the differences between who stayed in the two conditions, they were able to measure them. They said that a follow-up study that used the same ego depletion manipulation found that among the non-quitters, the people who persisted, those assigned to the depletion condition, the harder condition, writing without A and N, reported less fatigue even before the manipulation. So they were the people who went into it with more energy, less tired. Those are the 23% of people that stayed in. Compared to here, the 77% of people that stayed in, some of them were more tired. They weren't all the least tired, the most energetic people. So you're already getting a confound there. So that's more obvious in these cases where there's really big differences in dropout rates. But causal inference, so the reason that's a threat to causal inference, right, is that it could be their tiredness before the manipulation that's causing any differences in the outcome variable, not the manipulation itself, because you're getting different kinds of people staying in. But even when you have similar dropout rates, so here, where if you're asked to recall a past episode where you were in a powerful position, about a third of people drop out. If you're asked to recall a past episode where you're in a powerless position, about a third of people drop out. But there's good reason to think, right, just based on common sense, that different people are dropping out. Who finds it hard to recall a time when they were in a powerful position? Probably people who are relatively low status in their jobs and in other parts of their lives. Maybe they're younger, maybe they're less experienced. Who finds it hard to recall a time when they were in a powerless position? People who are very advanced, very high status, probably have more experience, etc. So you're ending up with different kinds of people in the two conditions, which the whole point of random assignment is to rule that out, right? The whole point of random assignment is to make sure that on average, people in the two conditions are the same. Now you introduce different reasons for people dropping out and you get groups that are different, who were different to begin with, right? That's the problem. These are pre-existing differences between people that affect whether they stay in or not. And so that pre-existing difference could now be a cause of any difference in your outcome. Then they did some really clever experiments showing that this can lead to completely ridiculous effects. So for example, they did an experiment where they asked people to list either 12 happy events from the past year, which is kind of hard to do, or 4 happy events from the past year, which is easier to do. And then they asked people, how hard was that task of recalling? And paradoxically, because of selective attrition, because of condition-dependent dropout, they find that people say that recalling 12 happy events from last year is easier than the people who had to recall 4 events from the past year say they had to recall. So that's right. So on average, this was rated as a 4. And I don't know the scale, sorry, maybe 1 to 7 on how hard it was. And this was rated less than a 3. And that's because all the people who found this really hard dropped out. The people who found this really hard also dropped out, but there were fewer of them. And in the end, the people who stayed in, the 30% of people who stayed in this condition were the ones who didn't find it all that hard to think of 12 happy events from last year. So it leads to this paradoxical effect. And if you don't pay attention to this, you could think, oh, look, people, find it easier to recall 12 than 4 happy events. Another ridiculous one they did was they asked people to either describe how applying versus not applying eyeliner makes you feel, or describe how applying aftershave cream makes you feel. So you can see what they're getting at here, maybe. Who's going to drop out from having to write an essay about applying eyeliner? Who's going to drop out from having to write an essay about applying aftershave? Similar percentages of people drop out. Then they ask them their body weight. And you would conclude that being asked to write about applying aftershave makes you heavier if you stuck with the causal inference of traditional experiment, right? We randomly assign people to write about either eyeliner or aftershave. And look, their weights were really different. So writing about aftershave makes you heavier. Of course, it's that heavier people are more likely to have experience wearing aftershave, applying aftershave, so they're more likely to stay in this condition. Lighter people tend to have more experience applying eyeliner. It's correlated with gender identity, probably. Okay, so then they say, yeah, but we did this on purpose to show how preposterous the effects can be, but most of the time, you're going to get effects that you predicted, right? You did the study for a reason, you manipulated your variable, you think it's going to have an effect on the outcome, you observe an effect on the outcome, and you think, great, my theory is right. But if you're not careful, actually it could be something else causing the effect and not your manipulation. And this is still something, even though this paper's been out for a while now, I don't see a lot of attention to it. So when I'm a journal editor, this is something I often ask researchers about. They don't report attrition, they don't report, or they at best they think, oh, well, we report that we got similar levels of dropout or attrition in both conditions, so we're okay. You have to go back to them and say, no, especially if it's high, then even if it's the same percent in both conditions, it can be a really big problem. If it's low, if it's in the single digits, it's very unlikely that like 5% of people dropping out, even if they're a very different kind of 5% in the two groups, that is less likely to lead to a spurious causal effect. Okay, so here's another quiz question to practice. Which of the following is an example of how selective attrition can be a threat to internal validity? If participants drop out of an experiment randomly, no, that's not a threat. If participants drop out of an experiment before being assigned a condition, no, it's not a threat because it can't have been something about the condition if they drop out before being assigned to condition, so that's okay. It's basically, you know that it's random across the conditions if they haven't even been assigned to a condition yet. If they drop out after being assigned a condition, but you know somehow, I don't know how you would ever know this for sure, but sometimes you could have some evidence that they're dropping out for similar reasons in both conditions. Not a problem for causal inference if you could know this. When it is a problem for causal inference is the fourth one. If they drop out of an experiment after being assigned to conditions, and you can't rule out the possibility that they might be dropping out for different reasons. So you don't actually need to know this. It's just if it's possible that they're dropping out for different reasons, which usually it is. Usually you can't rule it out. So then if people are dropping out after being assigned to condition, you have to worry about your threats to internal validity. Okay, so we spent a lot of time on internal validity, especially in the case of experiments, but I do want to remind you that experiments are still better for causal inference than measuring all your variables. So it's best to use manipulated groups, but you still need to watch out for confounds and selective attrition. If you must compare existing groups, you can't manipulate your variable. You have to really seriously consider alternative explanations, threats to causal inference, specifically third variables, also sometimes reverse causality. Okay. Any questions so far? Okay, and as I mentioned, I skipped construct validity because I'm assuming you covered a lot of the important factors there last week, but it's also always important in testing for differences and generalizing populations, et cetera.
I have two questions. The first one is, in the example you showed on Google, on the A/B testing, isn't it better that if that happened, because that's gonna happen also in real life?
Yeah, so that's a good question. So when there was the confound of it taking longer to load, it turns out that they called it a glitch. They said that it doesn't have to happen in real life. So they fixed that problem and they managed to make it so that you could imagine artificially slowing down the 10 results per page to make it even with the others, but that wouldn't be really relevant because if in real life it would be faster, then that's a natural advantage of the 10 results per page. But the way they described it sounded like it doesn't have to be that way. And they had some glitch that was making it take longer to load in the 20 and 30 that they could actually eliminate. So if that had been driving in the effect, it would have been good to know, because maybe people prefer 20 or 30 results if they can get it as fast. And if they can get it as fast, you want to know that. But yeah, you're right. If it had been just inherent to 20 or 30 results, it just always takes longer than 10, then it's not a confound. It's part of the manipulation, right? It's inherent to the options. Yeah, that's a good point.
The other question I had is, how do you, like, when you measure things that are not manipulated, such as like the invisible gorilla experiment, for example?
The gorilla experiment?
Yeah, the one with the basketball.
Yeah. Did they not manipulate? I don't
No,
remember.
They just show it to them and some people see it and some people
Okay,
don't.
okay.
How do you report that? You just say the number, 50% of.
Oh, yeah, so that's actually a case of generalizing to populations, not testing for differences. If they weren't comparing groups. So this is a case where people were asked to watch a basketball game and maybe they had to count passes or something like that. There was some task they had to do that took their attention. So then they had someone dressed in a gorilla costume walk across the court during the basketball game and people didn't notice. But that doesn't sound like they're looking for differences. Maybe there were versions of the study where they had different.
They're not. That's the
Yeah.
question.
So if in that case, you're just interested in what percentage of people do X, in this case, notice the gorilla. So that's not a testing for difference situation, it's a generalizing to populations. So there you would report, the percentage, you might report the precision. So like a margin of error around that percentage or confidence interval. And there you would be very concerned with construct validity. So is it specific to the gorilla, that way of operationalizing intentional blindness, or is it more general? You'd want to do the study with other things too. You'd be concerned about external validity a lot, and we're going to talk about that later, and statistical conclusion validity, but internal validity is irrelevant. Yeah. So there are a whole set of studies where internal validity is irrelevant. If you're not making a causal claim and you're not hinting at a causal claim, then internal validity is irrelevant. When there are two variables, it's almost always relevant. If there's more than one variable, it's almost always relevant, because usually the reason you're interested, even if it's just an association between two variables, the reason you're interested in that association is because there might be a causal effect, almost always. There are a few exceptions, but almost always. Authors like to deny that. They say, we're just interested in the correlation, and I've done that in the past. Now I try to be more honest, say, at this stage, we're just interested in the correlation. But of course, the reason we're interested in the correlation is that there might be a causal effect, which we would want to understand down the road. Right now, we just want to understand the relationship. Okay. Any other questions?
With the dropout rate table, was that for a random allocation, like manipulated groups?
Yes. So all of those were experiments with random assignment to manipulated conditions.
So is that why in the power one, the dropout rate's very similar, because there's like random allocation within the groups?
But in the ego depletion one, it was random allocation too, and the dropout rates are really different. So it depends on how similar the tasks are. So in the ego depletion, it's intent, like the point of ego depletion is to deplete people more in the experimental condition than the control, so they got a harder task. So it makes sense that dropout was higher in the harder condition, 77% versus 22. But you'd still need to find a way around that if you want to do research with good internal validity. In the power case, it's interesting that the two dropouts were similar. So there were about as many people that found it too hard to think of a time when they were powerful as people who thought it was too hard to think of a time when they were powerless. But it's not, I wouldn't have known that that would be the case ahead of time. It could have been different dropout rates.
Yeah.
I don't know that there's a good way to predict when the dropout rates are going to be similar versus different. But the more important point is that it almost doesn't matter, because if the dropout rates are high, whether they're similar or different, you have to worry about selective attrition. Yeah. If the dropout rates are different, you already know that they're dropping out for different reasons, because they wouldn't have different dropout rates. If they're the same, maybe there's still a chance that they're dropping out for similar reasons, as at least they're dropping out at similar rates, but you still can't know that for sure. There's still the threat that they're dropping out for different reasons. Any other questions? Okay, so let's move on to external validity. So we're still sticking to testing for differences here. We're talking about a case where you have at least two variables. You're interested in either their relationship or their causal effects of one on the other. And so we're going to talk about two different kinds of external validity. One is population validity, which is the representativeness of your sample of participants or respondents to the population you want to generalize to. So getting a representative sample of the population you want to generalize to is often quite difficult. In fact, it has become, I would say, nearly impossible. So before the internet, it was not impossible, just very expensive and very hard to do random digit dialing. So before cell phones and stuff, you would just get a list of all phone numbers, randomly select phone numbers, and call those people and do an interview with them. For example, so national election studies in the US would do surveys like that to poll people on their preferences for political candidates and policies and so on. They would invest a lot in like just harassing people basically until they answered the phone. So they had basically no dropout, nobody who, if you were randomly selected, they got a hold of you somehow. You could still refuse to participate in the study, so there was still some threat to representativeness there. But nowadays, I think it's basically impossible to actually, so even if you can identify the whole population, let's say I'm interested in University of Melbourne students, I only want to generalize to University of Melbourne students, I could get a list, maybe, like in theory, I could get a list of every University of Melbourne student and I could randomly select students to invite to participate in my study, but to actually get them to participate these days, right? Phone calls, text messages, people screen all of those now. There's almost no way to guarantee that you will be able to approach that person and invite them into your study, much less that they'll necessarily participate. So what's more common now is people use weighting to create estimates that mimic what you would get with a representative sample. To even be able to do that, you need to get close to representativeness. You need to make sure that you're sampling all the different subgroups. If you don't have anybody from a particular subgroup, you can't weight their answers to make it a representative sample. So it's really, really hard, maybe almost impossible. The exception would be if your population is really small or really, really well defined and a really, like, let's say your population is people who participate in a particular Facebook group. You're really interested in members of this Facebook group, and they're all really invested in their identity as members of that Facebook group. Then if you randomly contact them and say, I want to study you because you're in this Facebook group, probably almost all of them will say yes. So if you have that kind of population, you might be able to get a representative sample. But if you have a very broad population, like an entire big organization, a country, you know, the human race, it's going to be basically impossible. So convenience samples are very common, they're often accepted, but it's a huge sacrifice. And as we talked about earlier, it's something that people often talk about as a limitation of their work. But again, I don't think they take that limitation quite as seriously as they should. So this is something basically we all acknowledge, we all say, and then we do very little about, but it is a real threat. And it is something that we always have to ask ourselves. And here again, we have to use common sense and reasoning about what are the likely selection biases. So let's say, for example, recently we did a survey of social and personality psychologists asking them about their research practices. And we wanted to know, do they think that we're doing good research in our field, et cetera. And the email came not from me because we knew that that would bias people too much because I'm pretty outspoken about my opinions about psychology research needing to improve a lot. So we had the email come from another member of my lab. So we sent emails to authors of recent papers. So we're trying to get a representative sample of people who have published recently in psychology. But we got a response rate like very many people in the single digits, like 5 or 10%, which is very common for convenience samples. Even if you start with a representative sample of the population, if you invite people, often you'll get, you know, less than 10% opting into your study. So then we had to ask ourselves, okay, thinking logically, what kinds of people are more likely to opt in? People who have more time, first of all, that's almost always the case, right? But also in this case, like probably people who have strong opinions about this topic, and maybe people who share our opinions, even though we kind of tried to hide what side of the debate we're on, it's probably not that hard for people to figure out. Many people probably already knew. And so we had to say in our discussion section, we likely oversampled people who think that psychology needs to improve, who thinks it has problems and so on. But we don't know to what extent. So it's really, really hard to come up with an accurate estimate of what the true population belief is. So this is often a really big limitation that we can't really overcome. And to go back to the point earlier, like there's some cases where if you can't have good population validity, then everything else doesn't matter. If your whole goal is to try to estimate the frequency of something, which we'll get up to later, in this cases where you just have one variable and you want to estimate what is the average level of that variable or how many people have that thing, then this kind of validity is absolutely crucial. Another aspect of external validity is basically everything else you want to generalize to. So often we don't just want to generalize to other people. We also want to generalize to other ways of studying this, other contexts, other cultures, other times. And all of that, I'm going to put under the broad umbrella of ecological validity, but really that might be even too narrow of a label. The most relevant often for applied research is going from lab to field or from a hypothetical to a real world scenario. So all these power studies, for example, where they ask people to recall a time when you were in power and then they measure some dependent variable, is that really the same thing as having power, right? That's the causal claim they make in the end. Forget about selective attrition. Let's say nobody dropped out of the study. If you find that having people recall a time and write about a time when they were in power makes them, let's say, less compassionate, I don't know, compared to people who thought about a time they were powerless, is it really the case that we can conclude that having power makes people less compassionate? Is writing about a time that you were in power the same thing as having power? That's an ecological validity problem. You're going from this kind of not quite hypothetical, but not very realistic manipulation to this very rich, complex, real world variation. Yeah.
How's it different from having construct validity?
Yeah, so it's related to construct validity because you're putting a label on your construct that's much broader than what you really should. So it is, yeah, that's a good point. You could construe this as construct validity, saying you didn't really manipulate power, you manipulated like recalling a time that you were powerful or something like that. So sometimes, yeah, just relabeling the variable might take care of the problem. The problem is, let's say you relabel the variable so you're accurate in what you measured, but then in the discussion section, you still go on to generalize to real, like, we think this means that people who actually have more power do this, then it becomes an external validity problem. Like you did the study, you interpreted the study correctly, but then you're generalizing from your study to something broader.
Is there ways that you can say that this could inform things, or is that still a problem?
I mean, you can say what you can get away with a lot. So the question isn't so much what you can get away with, but like what it's responsible to say. Yeah, I mean, this is the problem where
could go further into this.
Yeah, this is a case where I think the author's own biases are be very hard to overcome, right? So if you're doing this research, it's because you believe the theory and you want it to have some application. You don't want to think your research is useless. So almost always the authors are going to be able to make a pretty compelling case that their research is relevant, even if it doesn't directly speak to it, is relevant. As a reader, I would be skeptical of that because they're absolutely motivated to think that. They came in thinking that anyway, nothing was going to change their mind, probably. So I would read it with a skeptical slant. Yeah. Did you have a question back there? Okay, yeah. Sorry, I didn't catch that. Yeah. Yeah, I mean, I wouldn't worry too much about the categorization into construct or external validity. I think it's true. These often aren't very neat and tidy categories. They do bleed into each other. But I would say that it's often the case that these kinds of issues are both construct and external validity, because even if authors don't explicitly state they want to generalize, implicitly they always do, right? No researcher thinks, I only care about this as I'm measuring it in this study. They care about the broader abstract construct of power or whatever. So let's say they're manipulating mood, and they manipulate mood by showing people a happy video or a sad video. Even if they don't explicitly say, we think that therefore the effects we observed would happen with other ways that people's mood changes, not just a video. They don't need to say it explicitly. It's often very strongly implied. Otherwise, why would they do the research? It's almost never interesting just to know if the effect is there with the specific way you operationalized it. Almost always you want to know, you want to generalize to the broader construct. Yeah.
To make inference, to eventually come to a point where we're making inferences about abstract concepts like power. We have to find all the variables involved in order and have this model in order to make.
Yeah. So the question is, to really make a generalized statement about a construct like power, what effect power has on people, would we need to find all the ways of operationalizing it? So this is one of the reasons why people say actually we should value non-experimental work more, because we can measure power in a much more rich and nuanced way in the real world if we don't manipulate it. Yeah. And so if we went out and measured different people's level of power in many different contexts, at work, at home, in their profession, in their hobbies, and their whatever, how much power people have, how much, it's bit easier to capture the full construct of power if we're not manipulating it. But really in the end, what we want to do is triangulate. So if we want to know if power has a causal effect on, say, compassion, we probably want to do some studies where we manipulate power. We probably want to do that a few different ways that are as different from each other as possible, not just tweaking one manipulation a little bit. And we want to do observational studies where we measure power and look at its correlation with compassion, and also measure other variables that could potentially be third variables and rule those out. All of that. Really, if I want to, in the end, make a conclusion about how power affects something, a causal claim in the real world, I probably need all of that kind of evidence. I mean, one conclusion we're going to come to is it's very, very hard to ever make an interesting claim, right? Like, because interesting claims probably need to have pretty good validity on all four of the validities. And you're almost never going to get that in a single study. It's very, very rare. Maybe impossible in the social sciences, I would argue. So you're almost always making compromises. And so one of the most common compromises, one that you'll see people talk a lot about, is between internal validity and external validity, because of this problem of external validity. That in order to have good internal validity, you want to manipulate things, and you want to manipulate them well in a really controlled setting, which usually means doing things in an artificial way, in the lab, in a really, really controlled setting, with a manipulation that's really clean, which often means pretty anemic, pretty far from the broad, rich, complex construct. You're translating it into something really simple and narrow. And so you do that to have experimental control, to have good internal validity, but you're sacrificing this part of external validity. So there's often this trade-off, and that's why I would say if you're really interested in a causal claim and generalizing it to something broad, then you probably need some experiments and some observational studies of high quality in both cases, because of this trade-off between internal and external validity. Any other questions? Okay. Okay, so for external validity, I would say the key takeaways are that representative samples are ideal, but almost never achieved. Convenience samples can be okay if it's similar to the population of interest, or at least we treat them very often as okay, at least in the context of testing for differences. Again, we'll come back to cases where we're interested in just generalizing one variable to a population. It's different. But in the context of testing for differences, we tend to accept convenience samples, but you can still do better and worse convenience samples, right? You should still put in effort to get a sample that has diversity on the dimensions that your population has diversity on. Make sure that you're sampling the different subgroups of your population. Ecologically valid designs are important. They can be challenging in testing for differences, especially because of this trade-off where internal validity is considered extremely important, less important than external validity when we're testing for differences. So often we trade off external validity for internal validity by doing a really contrived, controlled experiment. Okay. So this is where I think we should take a break. And let's come back in about 15 minutes, so 10:45 or so, 10:45 plus or minus a few minutes, and we'll pick up there.
I went to UC Davis.
Oh, wow.
Yeah, from undergrad. So
When
this
were you there?
2018 to 2021. I graduated a year early. Really?
Yeah.
That's
Did
crazy.
you study psychology?
Yeah, psychology and sociology. Yeah.
Do you work in any lab on site?
I did social and personality lab with Richard Robbins
Oh, yeah.
and Haley Wilson.
Yeah. So the paper that I talked about where we looked at how often people use ad hoc measure, that's what Kate did.
No,
She's the professor.
we published. I think she's a professor now, but we worked on like a research project with them over COVID, so it was all on Zoom.
Yeah.
We ended up like publishing a paper.
Wow.
Yeah.
What's your name?
Brenna.
Brenna?
Yeah, but I was like one of our readings this week was like one of like it was like UC Davis. I think it was like
Yeah,
some
yeah.
paper that you collabed on. I was like, what are the odds like in Australia? And I'm reading about Davis.
Yeah.
Yeah.
I have that one of the authors in that paper, Sarah Schiavone, who was a grad student at UC Davis.
Yeah.
At the same time, she's here now as opposed to.
That's crazy.
Yeah.
Yeah, well, we should do like a little Aggie reunion.
Yeah,
That'd be sick. Yeah, yeah. So you worked with Kaylee and Richard?
I was colleagues with Rick, and then
Okay.
so Kaylee was his grad student, and so
Yeah.
I ended up collaborating with her on.
Yeah, that's crazy. That's such a small world.
Yeah, that's nuts.
Yeah. That's cool. So what brought you out to Melbourne?
My partner lives in Sydney, so I moved to Australia to be.
Okay. Yeah, yeah. How do you like living here?
Yeah, I love it.
Yeah,
Yeah.
it's
How about
great.
you?
Same. I was supposed to do my third year at the University of Sydney,
Mhm.
and then COVID happened. So ever since that, I was like, gotta get out to Australia. And like this program's like really unique. Like we don't really have anything like it
Yeah,
in the
there's not, I
States.
haven't seen much like that.
So it's cool. It's like perfect, like what I want to do, and it just worked out. Right. Yeah.
Are you planning to move back to the States? or-
I think that I want to get a job here for a bit, especially since like I'm making all my connections here.
Yeah.
I do love it a lot, like in person. Like it feels like home, but like a safer version of it.
Yeah,
In a way. But yeah, so do you live in Sydney or?
I do live in Sydney actually,
Okay.
so I just flew in last night and staying a week and a bit.
Yeah, yeah. How do you think Melbourne compares to Sydney?
Yeah, it's interesting. I have a lot of opinions.
Yeah.
I tend not to go into it too much with Melburnians
Yeah.
because they are very proud.
Yeah, yeah,
But it's funny, if you talk to people in Sydney, like I'll tell people in Sydney, "Oh, I'm going to Melbourne," like, "Oh, I love Melbourne."
yeah,
And then you talk to people in Melbourne, they're like, "Really?" I'm like, even the idea that the weather's better in Sydney, they're like,
Yeah.
"Is it though?" I'm like, yes.
I feel like that's like like this debate of like NorCal
Yeah.
and SoCal. Like everyone's like, man, it's fair. Like there
Yeah.
has to be some.
But it's funny because I was always on the NorCal side of that debate. And
Yeah.
now that I live in Sydney, I'm like, maybe people in LA have a point.
Yeah.
I was always like, I don't.
Is the weather truly better in Sydney?
Yeah, it's so much better.
Yeah, it's like the one thing that I just have not been enjoying here, but other than that, the city's great. Like
Yeah,
I love the University of Melbourne, great school.
yeah.
Kind of reminds me of Davis, like in a lot of respects,
yeah.
just like campus wise,
Interesting, yeah.
lectures.
I don't have a sense of what it's like for students here.
Yeah.
I haven't that much here,
Yeah.
especially with COVID and all that.
Yeah,
Yeah, like, I mean, I feel like I get the best of both worlds. So I feel like
Yeah.
many of the best things about Melbourne are the intellectual side and
Yeah,
stuff like that.
yeah.
But then I get to live in Sydney and have the weather and
no, it's
natural
perfect.
beauty.
Yeah.
and-
So what are you doing out in Sydney?
I just work from home there and then I
Okay.
come here when I need to do stuff. in
Yeah,
person.
That's cool. Yeah. Well, it was nice to meet you. That's just
Yeah,
I just
great to
I just
meet
had
you.
to say something.
Yeah, we should get a.
Yeah,
group of Davis
100%. I'd be
together,
really keen.
yeah.
Yeah, sweet. Yeah, we should do it. All right. Well, we can exchange contact.
Okay,
Yeah.
sounds good.
It's Friday? Oh, it's Friday. I'm not. Oh my God. I was gonna come here. No, I was gonna. She told me to do it. Well, I was gonna come in today and ask her. Let me see if I can. That's really. Actually, yeah, it's wrong. Every year for now.
Oh my God. Yeah.
Okay, let's go ahead and get started again. So make sure that you've signed in. If you haven't signed in, I think that's the signing clipboard at the back there. Okay, so we have one validity left, but it's the most technical and one that I could go on about for ages. So we will be here until the end of class today. We're going to be talking about statistical validity. And again, we're still talking about testing for differences for now. We'll get to generalizing to populations, the other kind of research, just at the end of the lecture today. Okay, so in the context of testing for differences, what does statistical validity, sometimes it's called statistical conclusion validity, what does that look like? Okay, so when we're testing for differences, let's say we're comparing two groups, maybe they're measured, observed differences, maybe they're manipulated groups. We might conclude one of two things. We might conclude there's no effect. So in the case of difference between groups, that would mean there is no difference between groups. The null hypothesis is true. I'm sliding from no significant difference to the null is true here. We're going to talk about that in a bit. Actually, what we should conclude here in the context of null hypothesis significance testing, p-values, statistical significance, et cetera, is that we didn't detect a difference. So we shouldn't conclude that the null is true. We should conclude that we couldn't reject the null. Hopefully, a lot of this is familiar from your undergrad. I'm going to repeat a lot of stuff that you learned in undergrad, partly because in my own experience, it's something we need to hear over and over again, and then I'm going to build on it. So I want to make sure that we all remember all this stuff. The other possible conclusion, you do find a difference between groups and you reject the null hypothesis. You say the null hypothesis is false. And then often we make the leap from there to saying that therefore our alternative, our research hypothesis is supported. But again, there's a leap there from rejecting the null to accepting the research hypothesis. We're making a conceptual leap. Technically, all we should be doing, statistically speaking, is saying either we could reject the null or we could not reject the null. And we'll talk a little bit more about that. But practically speaking, what people end up doing is if they don't detect a difference, they see the groups are equal, they accept the null. If they do find a difference, they reject the null, but they also say, therefore, my research hypothesis is true. I found support for my theory. So very often we run a study because we do think there will be a difference between the groups. We do think our manipulation will have an effect, or that the measured existing groups will be different on our outcome variables. So we're hoping to be able to draw this conclusion to reject the null and therefore say that our research hypothesis was supported. So because those are the two possible conclusions, either we fail to reject the null, often we mistakenly accept it, or we reject it. That means there's two kinds of errors we can make, statistically speaking. So we can make a false positive error where we reject the null, we think we see a difference, but actually there's not a difference there. So here this dog thinks it sees a bone, but actually it's a stick. So that's called a type 1 error in null hypothesis significance testing. I don't care if you remember that it's called type 1, but you should remember that's called a false positive, right? A false positive is you think you see a difference or an effect, and in fact, there's not one there. And the other kind of error is if you conclude there's no difference, you fail to reject the null, but actually there is a difference in the real world. And the truth is that there is a difference. It just didn't show up in your sample, or it wasn't statistically significant in your sample. That's called a false negative. So you think there's nothing there, you think there's no effect, you fail to reject the null, but actually there is a difference in the truth of the matter is that there is a difference. So I'm talking about as if I have like a God's eye view on the world and I know what the truth of the matter is, but of course we don't know. But I'm going to now talk a little bit about, to talk about errors, we have to assume there's an underlying truth, and that, from the perspective of talking about errors, we could stipulate what the truth is. In reality, all we know is whether we got an effect or not, whether we got a significant difference or not. So we know after we run our study, we analyze our data, we either find a difference because we get a statistically significant result, we say therefore the groups are different, or we say we can't tell if there's a difference, the difference is not significant, we can't reject the null. Often again, people here end up accepting the null. They say there's no difference. Now I know that there's no difference, that's an error. But okay, so now let's cross that with as if we knew the true state of the world. Let's give ourselves omniscience just for the purpose of talking about these things theoretically, and pretend we knew whether we live in a world where there actually is no difference, their manipulated variable doesn't affect the DV, or the groups are not different on your outcome measure, or do we live in a world where there is a difference? Okay, so when we cross those two things, we get two cases where you're drawing the correct conclusion. So if you don't find a difference and there is no difference, that's a true negative. If you do find a difference and you live in the world where there is a difference, that's a true positive. But again, we never know which column we're living in. We only know which row we end up in. So in each row, there's also the possibility of an error. So if we don't find a difference, either that's a true negative or that's a false negative, and we don't know which. If we do find a difference, either that's a true positive or that's a false positive, and we don't know which. So what we want to do to increase statistical validity when we're using p-values is reduce the chances of errors. And so maximize the chances that we're in these two boxes. Of course, most people really want to land here. They want to find an effect. They think there is a difference and they want to find it. But if we do have to end up in the top row, we'd rather be in the top left than the top right. So we want to maximize the chances of having a correct conclusion. We also want to maximize the chances of finding an effect very often. Now I'm talking in this very kind of cynical, practical way. Really, we should just be motivated by the truth. We should want to find the truth, whatever it is. Realistically, very often we start off with a good reason to think that there is an effect and we want to find it. Okay, so let's talk a little bit more about p-values and how they help us get to these conclusions. So in the context of null hypothesis significance testing, which is what we almost always do in psychology, there's now increasingly more people using Bayesian statistics, but those are basically the two options right now, Bayesian or frequentist statistics. And if we're using frequentist statistics, we're almost always using null hypothesis significance testing. You don't need to know all that. Basically, you should be familiar with the idea of null hypothesis significance testing, which is what leads to a p-value. So here we start by assuming, and I put that in quotes because we don't actually believe this, that the null hypothesis is true. So we pretend for statistical purposes that we think the null hypothesis is true, which is not actually what researchers believe, right? They design the study, they're doing this research because they think there will be an effect, almost always. It doesn't have to be that way, but it just is in reality, practically. So we're adopting the position statistically as if the null hypothesis were true. And then we ask, if this were the case, if the null hypothesis were true, how unlikely is the effect I observed? So I measure maybe two groups, maybe people from New South Wales, people from Victoria. I measure them on their preference for beach vacations versus going to a museum. And I want to know if there are any differences between those two groups. So we're not talking about the causal inference now, just is there a difference here? Is there a real reliable difference? How do I know if it's just noise? Maybe they're the same, but actually they're, in my sample, I got slightly different means, but maybe the population is the same on their preferences for those vacations. So I'm asking, is any difference I observe, is it just noise? Could it just be sampling error? Or is it so unlikely under the null hypothesis, if there were no true difference, my observed effect is so unlikely that I'm going to reject the null hypothesis? That's the logic of null hypothesis significance testing. So we need to have a good understanding of sampling error. What do I mean by sampling error? Sampling error is just random error that happens just because, not because I did anything wrong. So you're just going to get variation in your data. And if you did the same study over and over again, you wouldn't get exactly the same result every time, right? So we don't expect the result to be exactly zero when the null hypothesis is true. It can vary just randomly around zero. So sampling error is what the variation in results you would get around the true result. So if we're assuming the null hypothesis is true, we're assuming the true difference between groups is zero. And if we did the study over and over again, we would often get results around zero, but not exactly zero. And so, and they would form a normal distribution around 0. So results very close to 0 are more likely, results further away from 0, one group being much higher or much lower than the other, are less likely. And every once in a while, we get a result so extreme that it's very unlikely under this distribution. And so we take this sampling distribution under the null. So this is a sampling distribution. It shows the sampling error around the true effect of 0. If we assume the null hypothesis is true, once I know the details of your study, I can simulate if the null hypothesis were true, what results would I tend to get if I ran your study over and over again? And this shape is the key shape in null hypothesis inference testing. It's the sampling distribution of the results under the null hypothesis, centered around 0. Again, we don't actually believe that the effect is 0. So we don't actually believe that our study is going to be picked out of this distribution. But we're starting with the assumption that it is to calculate the p-value. So under the null hypothesis, what would the results of our study look like if we pulled them randomly from any study in the sampling distribution? Most of the time they would be close to 0. And then we can calculate the specific, let's say I run my study, I get a result, let's say 0. The probability of getting a result at least as extreme as exactly 0 is 100%. 100% of results are as extreme as or more extreme than 0. But if I get a result out here, what's the probability of getting a result at least as extreme as this? It's however much area there is under the curve that's beyond that in either direction. Right? So if I get a result, I can compare my result. Let's say I get a result that lands out here, pretty big difference between groups. Group A is higher than group B. I can ask, what's the probability of getting a result at least this extreme if the null is true? It's however much of the curve is more extreme as or more extreme than my result in either direction. That's the p-value. So you find your observed results on this curve, and then you compute the proportion. How many of the results, how much of the area under the curve, how often are results at least as extreme as my results? So the p-value is answering the question, if the null hypothesis is true, what is the probability that I would get a result at least as extreme as the one I got? So in addition to teaching kind of regular big research methods classes, I also, when I was at UC Davis, taught a seminar that would meet every week with about 15 students. And one of the things I would do is every week at the beginning of class, I would ask a quiz question that everyone would have to answer, which is to define a p-value. And the term there is about 10 weeks. And by week 10, maybe half the class would get it right. It's extremely hard to remember the definition of a p-value. Even scientists, professors, people who teach research methods, sadly, get this wrong a lot. So there's a couple of things you can do to help you remember. One is that you always start with the conditional that the null hypothesis is true. Any definition of a p-value has to start with the assumption that the null hypothesis is true. You're calculating a probability in this world where the null hypothesis is true. We don't think we live in that world, but we're interested in the probability of our results in that world. We're saying in the world where the null hypothesis is true, how unlikely is my result? What's the probability of getting a result at least this different from 0, this extreme in that world? So that means that the smaller the p-value, the more extreme the result, right? If it's really unlikely, that's a result really far from 0. And in psychology, we've adopted this convention that if the p-value is less than 0.05 or 5%, we reject the null hypothesis. We say, my result would be so unlikely in this world that I don't think it came from that world. That's the logic. And we say, if it's 5%, less than 5% chance that you would get a result that small, that extreme, that big in that world, then I'm going to conclude that it didn't come from that world. That is not sound logic, right? I don't know if any of you have taken logic, but you can't conclude that just because something is unlikely that it didn't happen, but that's what we're doing. So we're taking a risk. We're going from it's really unlikely, less than 5% chance to therefore that's not what happened, something else happened. This result came from some other distribution, not from this distribution. And 5% really isn't that unlikely if you think about it, right? Like it's not a very extreme cutoff to set. So lots of things that are 5% chance happen pretty often. If you thought there was a 5% chance of it raining, you probably wouldn't take an umbrella, but you also wouldn't be completely shocked if it rained. Like it wouldn't be like, wow, that's the weirdest thing to ever happen. in sports, many results that have only a 5% chance of happening happen, 1 out of 20 times. That's the definition. So some of the time that we conclude this, some of the time that we get a p less than 0.05 and we reject the idea that our result came from that world, we're going to be wrong. Well, that's not true. Not 5% of the time. Some of the time we're going to be wrong. What percentage of the time we're going to be wrong is a very difficult question to answer. Okay, so we're making this leap. It's not really sound logic. It's not crazy. It's not a crazy leap to make. But people argue a lot about whether it should be 5%. So for example, I'm a co-author on a paper that says, no, actually it should be a lot less than 5%. We shouldn't be saying just because it's less than 5% chance, we're going to reject it. That's too loose, too easy to reject the null. We should make it harder to reject the null. We should maybe say 1%, or in this paper, we say 1/2 of 1%. But different people have different views about that. But we've accepted as a field to use 5%. Many social sciences use 5%. In the physical sciences, they use a much, much more extreme criterion because they have a lot less sampling error. Their distributions are much tighter and neater because they have a lot less error. They're measuring, partly because they're measuring things that are easier to measure, physical characteristics often. Okay, here's another quiz. Which of the following is a definition of a p-value? The probability that the null hypothesis is wrong, the probability that the data are consistent with the null hypothesis, the probability of obtaining an effect at least as big as the one observed if the null hypothesis is true, the probability that if the study were repeated, the null hypothesis would be rejected. So these are all relatively common interpretations of the p-value, but 3 of them are wrong. The only one that's right is C. That might feel easy now because you just saw the definition, but it won't feel easy even this afternoon. I bet if you don't review your notes and you just look at this quiz, well, maybe if it's in the exact same order and everything, you'll remember, but I could write a quiz that I bet that would be hard to pass to get the right answer this afternoon. So one trick, but I really rather you understood it deeply rather than using a trick, but one trick is to look for something about assuming the null hypothesis is true. It might not always be exactly in that language, but that has to be part of the definition. It's starting in this world where the null hypothesis is true, then we're computing some probability. You might think that these are also correct, but they're not. They're very common misinterpretations of p-values, but they're not correct. You cannot go from the true definition and conclude and derive any of these other implications of the p-value. Okay, so again, we're going back to the sampling distribution under the null. So here we have, this is centered around 0. This is if you repeated your experiment, the results you would get over and over again, most of them would be close to 0. In the 95% of the curve that's in the middle, that's non-rejection. We're not going to reject the null if we get a result in here. If we get a result out here, we are going to reject the null. And so our alpha, which is our cutoff for what the p-value has to be, in this case 0.05. So 0.05 represents a percent of the curve that's in the rejection region. And because we have symmetric rejection regions on both sides of the curve, then each of these is only half of alpha. So if alpha is 5%, 0.05, then there's 2.5% area on each side. That's because we're using a two-tailed p-value. So alpha is the critical p-value you need to get less than in order to get to call it statistically significant. So in psychology, we use 0.05. That means 0.05 is our alpha. You have to get p less than 0.05 to reach statistical significance. Okay, so that has an implication for our chances of making errors. So when we live in the world where the null hypothesis is true, we should land here, and we should want to land here, even though that's bad news for us. It's the correct answer when we live in this world. So when the null hypothesis is true, we should want to get a non-significant result because that's the accurate result. But we're tolerating the fact that sometimes when we're in this world, we're going to accidentally conclude that there is a difference. We're going to get a significant result and we're going to reject the null and we're going to be wrong. We don't know when we're living in that world, but when we're living in that world, that's going to happen sometimes. And we've accepted that it's going to happen 5% of the time, alpha percent of the time. That's what we're accepting when we set alpha. We're saying, what tolerance do we want to have for making an error when we're living in this world? Right. So if we lowered our alpha, we could make fewer false positive errors. We could say, no, I only want to make an error 1% of the time, or maybe even 0.5% of the time when I'm in this world. I'd rather be more cautious, have fewer false positives, and lower alpha. We could decide that as a field, but we haven't decided that. We're okay with 5%. Okay, that means that when there's no difference, when the null hypothesis is true, we're going to correctly fail to reject the null 95% of the time. But again, we don't know if we live in this world. All we know is what row we end up in. So sometimes we're going to end up in this top row. We're not going to get a significant result. And we're not going to know if it's the case that that was the right conclusion, or maybe there is something there, we missed it. Or we get a significant result, and we're not going to know if it's one of those 5% of the time when the null is true that we accidentally get a significant result, or if it's a true positive. We're just going to always assume that it's the correct answer. So when we don't get a result, we tend to assume that that's because there's no difference. When we get a significant result, we tend to assume that's because our theory is right and there is a difference. But we don't actually know that. Okay, so when we live in the other world, the error probabilities are completely different. They have nothing to do with alpha, or very little to do. They do have something to do with alpha, but not much. So when we live in the right world where the null hypothesis is false and maybe our research hypothesis is true, then the possibilities are false negative or a true positive. And there's no specific way we can set a threshold for saying we're okay with this chance of error, but we want this chance of getting it right, like we can in the other world. When we're in the null world, the null is true world, we can set what tolerance for error we want by changing our alpha. In this world, we can increase or decrease the chances of a false negative versus a true positive, but there's no like firm threshold. So we call the chance of a false negative beta. So remember, the chance of a false positive when we're in this world was alpha. The chance of landing here when we're in this world is beta. But we don't talk much about beta. Instead, we talk about its inverse. So here we had 5% with alpha. This was 95%. Here we have beta, and that's going to be whatever the rest of the percent is, right? So what we talk about is the chance of getting a true positive when there is an effect, and we call that statistical power. Statistical power is the probability of finding a significant result when there is an effect to detect, when the null is false. So you've probably heard about statistical power. The technical mathematical term for it is 1 minus beta. But like I said, we can't actually just set beta to something the way we can set alpha to something. All we can do is try to increase our statistical power, but we never know exactly what it is. It's not something we determine a priori like alpha. So I think we'll get into this a bit later, but just in case we don't get there, the main way that you can increase statistical power is to increase your sample size. You've probably heard that before, right? If you increase your sample size, you increase the chances of detecting an effect if an effect is there. That means if you're in the right world, the right column, then by increasing your sample size, you increase the chances of landing in the correct square, the true positive square, rather than the false negative square. There are a couple other ways, like using more reliable measures, studying a true effect that's larger. So the bigger the true effect is, the more likely you are to detect it. But those are often out of your control or harder to control. So the thing you can control is the sample size. Bigger sample means more statistical power, means less chance of a false negative, because these are add up to 1. Any questions about that? Hopefully some of that is familiar. You've heard some of these concepts before. Okay, so here's a quiz question. When we use p less than 0.5 as the cutoff for statistical significance, we're accepting that what? So are we accepting that when we get a significant result, it'll be a false positive 5% of the time, or are we accepting that when the null hypothesis is true, we'll get a false positive 5% of the time? One of these is a percentage out of a row, and one of these is a percentage out of a column. So the right answer is B. When the null hypothesis is true, we'll get a false positive result 5% of the time, because alpha controls your error out of this column. So when the null hypothesis is true, we can be guaranteed that we'll have only a 5% chance of a false positive. That's not helpful to us exactly because we don't know if we're living in that world. All we know is what row we end up in. So the p-value, the alpha 0.05, often gets misinterpreted as not a guarantee of a 5% chance of error in this column. It gets misinterpreted as a 5% chance of error in this row. When we get a significant result, there's only a 5% chance that it's a false positive. We wish that were true because it's way more useful because we know what row we're in. We don't know what column we're in. It'd be very useful to know how big of a risk I'm taking. If I interpret my statistically significant result as a true positive, what risk am I taking? What are the chances that it's actually a false positive? We don't know. There is no math that can tell you that answer. We can guess, and this is the topic of the replication crisis, that Many of us are saying, this is really, really, really high. Even though we fix it at 5% in this column, it's extremely high in this row. And that's our concern. That's why we're really worried. And there's a couple of reasons why we think it's really high. One is that when we try to replicate things and they fail, that suggests that those were false positives. They were significant in the original study. We try to replicate it. We don't get significant results. We realize, oh, we live in the left world. And that original study was a false positive. So it's one hint that we're not doing a very good job of keeping false positives down in this row. But it's a very, very common misconception that by setting alpha to 0.05, we can be sure that when we get a significant difference, there's a 95% chance it's a true positive and only a 5% chance of false positive. Wrong. It doesn't guarantee that at all. All that alpha guarantees is that when we live in this world, there's only a 5% chance that we'll get a significant result. But that doesn't help us again because we don't know when we live in that world. It's still nice to have that, we can sleep better at night knowing that. But in any given result we get, we don't know. We don't know. We know which row we ended up in. We don't know which column we're in. So what we really want to do is try to both minimize the chances of landing here and maximize the chances of landing here when we're in this world, so that overall, when we get a significant result, we can be fairly confident that it's a true positive rather than a false positive. Okay. So I'm going to review a few of the things I just said before I build on them. I know it's a lot. So remember we said there are two possible conclusions when we do test for differences. So one is that we don't detect the difference. We couldn't reject the null, right? Often we accept the null. We say there is no difference. That's risky. The chance of error here is a false negative. That actually we were wrong. Our study didn't work, but in reality there is an effect. If we did the study over and over again, most of the time we would detect an effect. We just got unlucky. And the chance of a false negative is beta%. We don't know what that beta is. We can reduce it by increasing our statistical power, namely by increasing our sample size. So if we really want to reduce the chance of this error, we should get bigger samples. That's one of the main things we can do to reduce this kind of error. And you would think that researchers would be very motivated to reduce this kind of error because we so badly want to confirm our research hypothesis. So you would think researchers would just always get really large samples, or anytime that's easy to do, they would get it. We've done some meta research now tracking sample sizes over time. And finally now in the last few years, we're getting to the point where people have decent sample sizes in their studies. If you look back to 2010 and earlier, the sample sizes were really small. And yeah, the studies didn't have a lot of statistical power. That small sample sizes are bad for all kinds of reasons, not just statistical power. But finally, I think we're starting to have a norm in psychology where you should have at least several hundred people in your study most of the time. It depends, obviously, statistical power is very complicated. How big of a sample size is big enough really depends on your question, and especially depends on your design. If you have a within subjects, within participants design, or between, if you're studying the kind of effect that is huge and everyone shows it, or a really subtle effect, etc. But for like nudging type research, for social and personality research, you need at least 200 people usually to have a decent chance of detecting an effect if an effect is there. Okay, so we want to reduce our chance of false negative error by increasing our statistical power, mainly by increasing our sample size. And then the other kind of conclusion we could make is that there is a difference. We did detect a difference. We got a statistically significant result. We reject the null and we say that our research hypothesis was supported. The chance of error here is a false positive error. So the error would be if the null is actually true and we reject it, it's a false positive. And the chance of that when the null is true is 5%. But that doesn't mean that when we reject the null, there's only a 5% chance that it's a false positive. Remember, think about the columns versus rows. Alpha gives you a guarantee about the column. When the null is true, there's only a 5% chance I will make an error and reject it. But it's not the case that when I find a difference, there's only a 5% chance it's a false positive. Okay. So we'll talk a little bit about ways to reduce false positives and false negatives a bit more. But I also want to point out there's another kind of conclusion we draw that's also statistical, besides rejecting the null or failing to reject the null or claiming that we found an effect or not. And that's how big the effect is. And here we're trying to get better at reporting effect sizes and 95% confidence intervals around those effect sizes. So a range of effects that we think is still plausible based on our results. And we can be wrong about the effect size, just like we could be wrong about there being an effect at all or not, right? So there's a lot of different kinds of statistical errors we can make. False positive, false negative are the two main ones. but we could also be wrong about the size of the effect. We could potentially be wrong about the direction of the effect. That would be a huge error. Like not only did we get how big the effect is wrong, but it's actually even in the opposite direction than we said. So those are two other kinds of errors that we could make, getting the size of the effect wrong or getting the direction of the effect wrong. And it's hard to quantify the chances of those errors. Larger samples help with this too, because larger samples make your estimate more precise. They shrink the 95% confidence interval. That you can rule out more and more effects. You get more precise estimate of the effect. Yeah, did you have a question?
I was just gonna ask, is there any way to get the direction of the effect wrong if you use just a one-tailed test?
No, you could get the direction of the effect wrong no matter what. You could just get really unlucky. Maybe in the real world, one group is higher than the other, but you get a sample where it's the opposite just by chance. Yeah. Yeah, one-tailed test, I won't talk about that much. You should almost never use a one-tailed test, in my opinion, because you're committing to ignoring any effects that go in the opposite direction. And usually if we think it's very unlikely to go in the opposite direction, but if it did, we would still want to know. And so to pre-commit to say, I'm going to ignore the results if they go in the opposite direction, I'm not even going to interpret them. I think that we should almost never do that. Different people have different views about that, but
Yeah, I remember that maybe using Bayesian methods, I don't know.
what methods? Bayesian, yeah.
Sorry. To tell you the difference between the true, like false negative, like you test for both. So
Yeah,
maybe
yeah. So Bayesian methods have a lot of advantages. And one is that they don't create this false dichotomy between, so they don't just, you don't just reject the null and fail to reject the null. You can actually accept the null. And they have other advantages too. I won't get into them, and you definitely don't need to know them for the exam or anything, but if you want to learn more about them, a couple of resources that I recommend. One is there's a book called Understanding Psychology as a Science. And the author, Zoltan Dionys, is a Bayesian himself, and he presents kind of the pros and cons of frequentist and Bayesian approaches, but from someone who's more partial to Bayesian approaches. There's also some good tutorials online by Alexander Etz, ETZ. He has some good tutorials on Bayesian methods. I'm not an expert enough to understand, but there are some advantages. I think the advantages are sometimes overblown. And I think that, to me, that changing the statistics to improve your research is kind of missing the point. I think most of the improvements we can make are in thinking better, more critically, more deeply, using better methods, et cetera. Changing the statistics, well, it might help save you from certain specific kinds of errors, but it's not a replacement for, better design and better thinking. In the end, I think you can do good research with p-values. You just have to think really critically about them. Same thing with Bayesian statistics. You have to make sure not to misuse them too. There are a few ways in which Bayesian statistics are harder to misuse, so easier to use correctly, but they have their own downsides too. Yeah, I think Bayesian statistics are becoming more and more common, so it's definitely something worth looking into and trying to learn a little bit about. And there are more and more resources out there for that. Okay. So now I want to add an asterisk to so I told you that setting alpha to 5% gives us one guarantee. It's not the guarantee we would like, but at least it gives us a guarantee that when the null hypothesis is true and we're in that left column, there's only a 5% chance of a false positive. Not as good as if we knew that when we get a significant result, there's only a 5% chance of false positive when we landed in that bottom row. It would be nice to know that. We can't know that. But even the thing we can know, the guarantee it should give us, it doesn't, because we don't play by the rules. So this is really at the heart of the replication crisis in psychology, and something that textbooks don't teach you, but is absolutely extremely common in how everyone does research. So the rules of null hypothesis significance testing are quite strict in order to keep p-values honest, in order to have that guarantee that alpha is going to protect you from false positives, keep them down to 5% when the null is true. You have to play by the rules, and we do not play by the rules. We're starting to get better at it. But in order for a p-value to be valid and to have that guarantee about the 5% error rate when the null is true, you have to either do only one significance test, calculate only one p-value from your analyses, or correct for multiple tests if you do multiple tests. Already we violate that rule almost all the time. Almost every data set we get for each research question will run multiple tests. We're going to try it this way, try it that way, or look at this, look at that subgroup. Already you're violating the rules. You no longer have the guarantee of a 5% error control rate when the null is true. Okay, so that guarantee has already gone out the window, but we do other things that violate the rules. So you're supposed to choose your test ahead of time. You can't choose your test after you've seen the data. even if you don't run a statistical test and get a p-value, but you see the data, you look at the distributions, you're no longer in a position to decide on your analysis and get a meaningful p-value. Once you know anything about the data, your p-value becomes less and less meaningful. The more you know about your data, the worse your chances are of keeping your errors, your false positive error, especially, under control. So you cannot peek at your data. You have to collect all your data and decide ahead of time when you're going to stop without looking at the data, and then you can analyze your data. And if you do only one analysis, or if you correct for multiple analyses, then your p-value has that property of letting you sleep at night, knowing that when the null is true, you're only going to get a false positive 5% of the time. Okay, so we often don't do any of those things. We'll collect data, we'll check the data, after a few weeks or maybe a few hours, depending on how quickly you collect the data, maybe even analyze it and see if we get a significant result. If we don't, we keep going. No, you're absolutely not supposed to do that. That is absolutely 100% against the rules. You're not allowed to do that. You could build in a control. So correcting for multiple tests, you could say, I plan to do that. After 100 participants, I'm going to stop. I'm going to analyze the data. I'm going to check the p-value. If it's not significant, I'm going to keep going. Then you change your alpha. So you can statistically model that you're going to do that and do it honestly, but you cannot just do it willy-nilly and just say, oh, let's check if the p is less than 0.05. Oh, it's not, let's keep going. Not okay. People do it all the time. You may have worked in labs that do it. It's not, that doesn't make those people horrible people. They don't even know that what they're doing is increasing their error rates, but it is. Yeah.
It's like, an example, like pilot testing.
So pilot testing is different. If you collect data, you analyze it, and then you don't use it again, you collect new data and you're going to analyze that data separately, that's totally fine. Totally fine. You just can't collect data, look at it, and then collect more data and include the data you looked at in your final test. Or if you do, you have to do some correction for that. You're increasing your chances of a false positive if you do that. Anything that gives you multiple stabs at a significant p-value from the same data is breaking the rules of NHST. There are ways to do it ethically and with keeping the error control. I'm making this a moral thing, but it's really more about you're just going to fool yourself and you're going to fool other people. So that's why, to me, it's a little bit of a research integrity thing, but most people doing it don't realize the statistical implications of what they're doing. They're not doing it with bad intentions, but it does lead them to fool themselves and then fool other people. So you only get one shot at analyzing any given data set for any given research question, or you have to plan ahead and build in safety nets, safeguards for fooling yourself, which they're not that complicated. There are good tutorials on how to do that as well if you want to do that, but people usually don't do that. They just do it haphazardly. Even if you don't peek at the data as you're collecting it, you collect the data, then you analyze it, but then you see in the analysis that there's an outlier and you think, oh shoot, I obviously should have dropped that outlier. Or maybe it's even more black and white than that. Maybe you see in the analysis that one respondent gave completely nonsensical responses, like there's no way anyone would take that person's responses seriously, and you should obviously drop them. That's a very difficult situation to be in because you've already analyzed your data, you've already gotten one p-value. If you do it again, it's breaking the rules of NHST. But if you don't drop that person, you're using really crappy data. So you're kind of stuck. It's not a great position to be in. What I would do then is I would drop that person, but I would report the statistical analysis both ways. And I would tell the reader that my p-values are a little bit threatened. There's a little bit higher risk of a false positive because I did another analysis after seeing the data. I still think it's the better analysis, but we should be a little bit less sure about it because I made that decision after seeing the data. And the reason is that it's a really slippery slope from obviously this participant should be dropped. Everyone would agree to, yeah, I think this participant should be dropped. I mean, look, come on, their answers don't make that much sense to let's drop the participant that if we drop them, it makes the study work, right? And the last one is fraud, but it's a very slow continuum from like nobody would ever object to me dropping this participant to I could be fired for dropping this participant, and we're almost always somewhere in that gray area. And I don't trust myself and I don't trust other people themselves to make that judgment when they're motivated, right? We have so many reasons to want the study to work, not just cynical reasons like pleasing our boss or being right or things like that, but also just intellectual. Like often we really believe the theory and we think it would be a shame to not be able to tell other people about this true thing we discovered just because of this one annoying participant. So if you have to change your analysis after the first analysis or after seeing your data at all, just have a lot of intellectual humility about it, be totally transparent about it, and tell your readers that they should believe you less because of that. And ideally, you could just redo the study, but now say ahead of time, we will drop participants if they show this pattern of responses because we think that means they're a non-serious responder or something like that. So that gets me to the solutions. So because of the replication crisis, we've developed a lot of new tools and new practices that I think do a really, really good job if you want to keep yourself honest and keep yourself from taking these statistical risks. So one is called pre-registration. So pre-registering your data collection analysis plan. When I started teaching this, I had to tell people what it was from scratch, but I think by now maybe you've heard about it. It's becoming common enough. It's still not most studies. So if you go and read a journal in psychology, most studies will not have a pre-registration, but more and more will. It'll be maybe 15–20% of studies now, I'm guessing. So this is where you write down your data collection and analysis plan ahead of time, and you put it somewhere that timestamps it so you can show that it was decided before you collected your data. So this would be including things like when you're going to stop data collection. So it could be after 200 participants, or it could be on May 3rd, or it could be whatever. But you write down how you're going to decide when to stop so that you keep yourself honest about not stopping based on the statistical significance. And how you're going to analyze your data. And this could be more or less detailed. The more detailed it is, the better protection you have against fooling yourself and against false positives. So ideally, you would write out the code you're going to use to analyze your data. And all you have to do when the data come in is hit run and run the code. We struggle to do that in my lab. We try to do that, but there are many projects where we don't know how to anticipate whether we'll need to transform the data if it's not normally distributed or other things like that. So a less detailed analysis plan is still better than none, but the less detail you have, the more then you need to be honest with yourself and with your readers that maybe you gave yourself room to fool yourself if you didn't commit to everything ahead of time. So that's what very often we do, is a compromise where we pre-register as much as we can. But both in the pre-registration and in the final paper that we publish, we say many of these decisions were actually not pre-registered. We made after seeing the data, so we're less confident about those results, and they would need to be replicated before we would be super confident in them. The beautiful thing about replication is that you're doing it for the second time, so you know what to anticipate better. So maybe you do one study where you don't pre-register, or your pre-registration is very vague. You figure out what you want to analyze in your data. You get a result, maybe it's very exciting, but you don't really believe it. You say, okay, now I'm going to do a study again. And this time I'm going to pre-register that I'm going to do everything either exactly the same way I did in the first study, or maybe you thought of a better way to do it, but at least you know what to expect and you can commit more fully to a really concrete analysis plan. And then that result I would trust a lot more than the first one. I remember talking to a researcher once who, in the early days of pre-registration, was really excited. She was telling me that she got this result and it was one that I, on the face of it, didn't believe. And she's like, yeah, we ran the study. We didn't get the result we expected, but we got this other really exciting result. And I was like, cool. Did you run a new study and pre-register that? And she's like, yeah, in the next study, we pre-registered that. We didn't get that. We got this other really cool result. I just kept going a chain like that. And to me, it was like, yeah, do you see what's happening? Like if you're never getting the thing you predict, but you're always finding something interesting, you're fishing for interesting things and you're finding them because you're giving yourself so many chances, but you're fooling yourself. Like if you're never able to get it again in the next study, when you constrain yourself to looking for that, that's a sign that you're fooling yourself. My previous research on self-knowledge also makes me just so skeptical that we cannot fool ourselves, right? It's so easy to fool ourselves. We have so many reasons, things that are pulling us towards finding something interesting, finding an effect, that I would just always assume that you as a researcher or the authors of the research that you're reading were extremely motivated to find something, to find a significant effect. They might not be aware of it. They might really think they were being totally objective and that they were taking all these precautions, but I would want to see the precautions. I would want to see the pre-registration, see how detailed it is, see if it matches the paper. So another thing that happens is people write a detailed pre-registration, they don't follow it. So they're supposed to report if they deviate from it, but they very often don't. So if there is a pre-registration, I wouldn't just assume, oh, it was pre-registered, great, I can trust it. I would go and look at the pre-registration and see if it matches what they did in the paper. So you're supposed to report any unexpected or unplanned results as exploratory, a new hypothesis that you've generated, and then confirm it if possible in a replication. That's what you're supposed to do. But again, I would not assume that researchers are going to do this. This is not yet the common practice. So see if the paper that you're reading actually did this. The other thing is that we can also hide results by just not publishing the study at all. So again, we're not doing this intentionally, but very often we'll analyze our data. If they don't come out how we wanted, we'll reanalyze them, see if we can make them come out how we wanted. And again, we're not conscious that that's what we're doing. But if nothing interesting comes out of the study, very often we won't bother to publish it. So another solution to this problem is that you should report all studies you ran that are relevant to a research question and all statistical tests you conducted, and pay attention to the entire set of results, not just cherry pick the best results or the best studies. As a reader, it's really, really hard to know. It's almost impossible to know if researchers did this. they might have other studies they're not telling you about. They might have other analyses they're not telling you about. So pre-registration helps you know if they plan their analysis and if they're reporting the analysis that they planned. But it can't tell you if there were other studies. I guess you could go and search if they have other pre-registrations out there and they didn't publish the studies, but they can also hide pre-registrations. It's complicated. So, I mean, again, most researchers aren't trying to hide anything, but they will convince themselves that you don't really need to know about the study that didn't work, because I know exactly why it didn't work. It didn't work because that researcher that ran that study was incompetent. And they will completely believe that. And so therefore they won't tell you. And they might be right, but they might not. And they owe it to the reader, in my opinion, to let you decide. But most researchers don't see it that way. And it's honestly not just the researcher's fault. Most journal editors will ask researchers to not report studies that didn't work, not report analyses that didn't work, that were not significant. So it's not researchers just choosing to do that. It's them responding to the expectations and norms in their field, including from journal editors. One of the reasons I love journal editing is that it gives you a chance to change the incentive structure, but to tell authors, no, I will actually punish you if you hide stuff, not if you tell me the ugly stuff. Okay, so to summarize the statistical validity section, so having a large sample size is really important because it helps you detect an effect when there is one there. It increases your statistical power. And then planning and pre-registering are crucial to reduce the risk of a false positive. So just to make this a little bit more concrete, when I said that setting alpha to 0.05 gives you this guarantee that helps you sleep at night, that when the null is true, you only have a 5% chance of landing here. And I said, doesn't help you sleep much at night because really what you want to know is the probability of false positive when you land in this row. But even going back to that guarantee that isn't worth much, even that we don't have, because what we're doing in effect without realizing it, so all these like analyzing the data multiple ways, etc., is we're taking a scenario where we should have landed in the top row. We should have gotten a non-significant result, but we reanalyze it or drop some participants or transform some variables. This is called p-hacking, by the way, so that we push the result into the bottom row, which might be okay if we knew for sure that we lived in the right world. Even then it's not great because we're exaggerating the effect size and has other problems. But especially when the null is true, it's increasing the rate of false positives way beyond 5%. And there have been some estimates using simulations showing that it might be as high as 60% based on the common research practices we do. All it would take for it to be 60% would be if researchers hide some studies. Again, hide sounds intentional, but don't report some studies. The studies they do report, they try a few different things, they drop a few participants, etc. Just a few things like that, combining a few things like that drives us up to 60%. So if it's 60% in that column, it could be close to 100% in this row. So that depends on both the false positive rate when we're in this world and also in how often we're in this world versus this world. So if we're often testing hypotheses where the null hypothesis actually is true, our research hypothesis is crazy and wrong, then we're going to have a lot of things in this cell and not many things in this cell. Okay, so all of this is to say that we had the replication crisis, meaning we tested a bunch of findings that were in this row originally and to see, can we get them again? Can we get them significant again? And we found that maybe half the time we couldn't. So we decided that they're probably false positives originally. They're not replicable. And we think that part of the reason that was happening is that people were breaking the rules of null hypothesis significance testing. So pushing things that should have landed in the top row into the bottom row unintentionally, unaware that they were doing that, that it had that effect. And so it was pushing the alpha to be a lot higher than 5%, even though we kept saying some 0.05 as if we had that guarantee, but we didn't actually. Okay. Any questions so far? I know that was a lot. Okay, so now we're going to do the generalizing to population. We're going to spend a little bit of time on that. So we spent tons of time on testing for differences. It's the more common kind of research you'll see, and it's more complicated in terms of the validities. Generalizing to a population is a little bit more straightforward in terms of the validities. So here, we're not interested in internal validity because we don't have two variables, so we couldn't be interested in cause and effect. We're interested in one variable at a time. What's the population level of that variable? What's the frequency, etc. So some examples of when you might want to use this kind of research is you want to know how many people commute to work by bus, for example, or what % of adults like to watch crime shows. How many pairs of shoes does the average Australian own? How much do teenagers search for mental health support online? How common is child abuse in Australia? So in this case, okay, so remember construct validity is always important. Internal validity is not relevant here. We don't have causal claims because we don't have a relationship between two variables to explain. We're just studying one variable on its own at a time. If someone did make causal claims, like all they did was measure one variable and then they told you what they thought the cause of that variable was, then we could talk about internal validity. Do they have good evidence for that? It wouldn't be coming from this study because they only measured one variable, but maybe they're drawing from theory or from other studies to make a causal claim. External validity is very important here. More important than when testing for differences, especially population validity is more important here than when testing for differences. This is at least something we tell ourselves, I think is true. The idea is that when you're testing for differences, you're not interested in exactly the absolute levels of one variable. You're interested in how the variables relate to each other. And that might be less sensitive to having an unrepresentative sample, to selection effects of who's in the study. But if what you're interested in is an absolute level of a variable, how many people commute to work by bus, how many people have experienced trauma, et cetera, then having a representative sample is extremely important. If you have any bias in who's in your study, that's going to throw off that estimate. So I'm going to take an example from the research world that made the popular media that I came across earlier this year. So the media article was that 62% of Australians report being abused and neglected in childhood. And it came across my Twitter feed with the headline, "Their air went out of the room, shocking new statistics on the abuse and neglect of Australian children." And so I thought, wow, that sounds like a really striking result. I went and looked, and this is from the media article report. They said that 40% reported witnessing domestic violence before the age of 18, 32% experienced physical abuse, et cetera. Now, my intuitions on this are not very well informed. I'm not an expert in clinical psychology. Some of you are, so you will have better informed intuitions than me, but it struck me as really, really shocking, like hard to believe shocking. So I went to look at the original article to see if I thought the methods were good and so on. And there were a lot of really, really good things about the original article. I have to say the sample size was large. There were a lot of people involved in designing the study, designing the measures, a lot of attention to construct validity, which it makes it all the more sad to me when I find a flaw that I think might be a fatal flaw, that so much work went into something that if it weren't for this one thing, it might have been a valid study, but then there's one thing that I think undermines the validity of the entire study. Okay, so let me tell you a little bit about some of the details of the method. So they did try to do a representative sample by getting a random selection of phone numbers, and the phone numbers that they selected received a text message with a link. They also called the people up if they didn't get a response and tried and kept text messaging them and so on. Ultimately, the person had to click on the link to do the study. The response rate was 4%. Like I said, this is very common in studies. In our studies, that's about, we get 5 to 10% very, very commonly if you just cold email people or cold call people. And the link that they got in the text message was australianchildmaltreatmentstudy.org. So I'm curious if anything, there's probably more than one thing that could jump out at you from this already. Does anyone want to nominate something? Yeah. So the title of the study being in the link and the content of the title of the study, right? So already with 4%, I'm worried about self-selection, right? It's definitely not a random 4%. You start to worry about that very soon. You know, anything under like 80%, you start to worry, or 50% at least, you start to worry that it's a very selective subsample that's not at all representative. But then when I saw the link, I said, oh no, like, why did they do that? Like, who's going to select into that? People who are concerned about child maltreatment, which doesn't mean that they have been maltreated themselves, but if you have, you're much more likely to be concerned about child maltreatment and want to help researchers who are studying it. So to me, that just like, their goal was to estimate the prevalence of these things. So I'm saying one variable at a time. They had more than one variable, but they're not looking at the link between the variables. They're looking at each variable on its own and its absolute level in the population. So a representative sample is absolutely crucial. It doesn't have to be a high response rate, but it has to be a representative sample. Almost all subgroups have to be equally likely to participate. Yeah.
I'm trying to think, what is the say given like an inference or like a daily that's also with that name?
Yeah.
Would that also be that band that you're gonna get like a 1K?
Yeah. So the question is, if it was like a bit.ly link or some other shortened link, then it might drive the response rate down even more. But the 1%, let's say it did drive it down to 1%, the 1% would be more representative. And I would, so we're actually going to get to that in a second, whether a smaller sample that's more representative is better or a larger sample that's less representative. So the selection bias that's introduced by this, and I could be wrong, I hope I'm wrong, everything I read in their message section suggested to me that this was the text of the link in the messages that participants received. Maybe let's really hope that that's not the case.
Yeah, so think about like my grandma that clicks on random links to get messaged to her. And the rest of the family, like younger people would have more, maybe like literacy
Yeah.
about not doing things like that.
Yeah, so
Like
there's,
not older people or.
yeah. So let's say they used a link that wasn't very informative, then we wouldn't worry about that selection bias, but we would still worry about other selection biases. So we would think, yeah, like people who have more time are gonna be more likely to participate. Is there any reason to think that people who have more time are more likely to have experienced or say that they've experienced child maltreatment? We'd have to think through that causal link. Age is another one for sure, that retired people probably have more time. Maybe older people are more likely to have experienced child maltreatment if norms are changing in the direction of less child abuse. But at least that you could measure. So you could measure age. If you think that's driving it, you could try to control for that. A selection bias where you're not even entering this, well, where you can't, yeah, I don't know, where the selection variable is the variable they're interested in, you can't really control for that selection bias. Yeah, but that we would want to think through other potential selection biases besides who's going to be more likely to click on the link because of the title. Yeah, anyway, for sure. Okay. Okay, so internal validity is not relevant. External validity, so you really need to have a representative sample or close. If you don't, you need to pay tons, like most of your paper should be dedicated to what are you doing about the fact that you don't have a representative sample. It should be mostly about what evidence do you have that your sample reflects the diversity of the population you're trying to generalize to? What have you done to weight the subgroups relative to their proportion in the population? How are you addressing any potential selection effects? That would be what I would expect the researchers to spend the most time discussing and interpreting their results. For a claim about generalizing to population about a single variable at a time, absolute levels of a variable, that's what I would want the most discussion of, because that's the hardest, I think, the hardest validity to get. Again, concert validity is also really important. So if the way they were measuring child maltreatment was not valid, that would be a problem too. And then statistical validity. So it's still really important, but I would say less than external validity. And it's also a little bit more simple and straightforward because there's no hypothesis testing. You only have one variable, so you can't really have a hypothesis about causal effects or things like that, relationships between variables. So instead, the main statistical finding is a point estimate, % or a mean or something like that, and a confidence interval or margin of error, something like that. And so here you can increase your precision. You can have a smaller margin of error, smaller confidence interval by getting a larger sample size. So that's pretty important. So for a different reason than in the case of testing for differences, but in both cases, larger samples are better. Okay, so when you want to know frequencies, proportions, levels, when you're generalizing to a population, like you want to know how many people commute toward a bus or things like that, the most important factors are having valid measures, constant validity, having a representative sample, external validity, and a large sample, statistical validity. And I would say probably these two are the most important. It's hard to say, yeah, like I said before, it's really hard to say what's most important, but external validity is uniquely important here more than it is for testing for differences. So that raises the question. So I'm saying you need, putting aside valid measures, you need a representative sample and you need a large sample. So what if you have to choose, right? Very often one comes at the expense of the other. I can get a large sample if you let me use a convenience sample, but if you make me get a more representative sample, it's going to cost me more time and money. I'm not going to be able to get as many people. So which should you do? So that leads us to a discussion of two different sources of variance, noise and bias. I'm going to make the connection back to this question eventually. So noise is a word for random error. So random error is not because you did anything wrong. You can't make it go away completely, but you can reduce noise by collecting more data. Because that error is random, if you get one participant, their noise might go in one direction, another participant, their noise might go in another direction, and by having those two participants, they cancel each other out. And there's a really cool demonstration we could do if we had more time, where we can show that by getting multiple measurements of something, we narrow in, when we average more and more measurements, we narrow in onto a more and more precise value. It's not necessarily the right value, because we're canceling out random error, but we're not getting rid of systematic error. So bias is systematic error. So bias is if people have a tendency to overestimate something, or if a scale is wrong in a particular direction. So I measure my weight, I get on the scale. It might be not at all noisy. It might give me the exact same weight every time. It's not a noisy scale, but it might be very biased if it's giving me the wrong weight. So bias is error that's consistently in the same direction. And so selection bias, for example, who opts into a study? If people are opting into the study because it's called Australian Child Maltreatment Study, that's a systematic bias. It's systematically favoring people who are more likely to report certain levels on the variables of interest. It's not random. So I can increase my sample size as much as I want and get rid of random bias, random error, noise, but I won't be getting rid of systematic error bias. The only way you can get rid of systematic error, and is only the systematic error in terms of who's selecting into your study, is by having a representative sample. There you get rid of any systematic error that's coming into, by who's coming into your study. You could still have systematic error if your measures are bad, other sources of systematic error, but about who's in your study, the representative sample eliminates systematic error about that. So large samples reduce noise, but not bias. A large unrepresentative sample gives you a precise estimate, but it could be wrong, could be inaccurate. So we don't want to emphasize large samples to the point where we're getting worse large samples, less representative large samples. So representativeness of the sample reduces bias of the sample. So a small representative sample gives you an imprecise estimate, but likely in the right ballpark. So you'll be able to say, I think it's between 3 and 18% of people have experienced child abuse as in their past, or maybe it would be like 3 to 35. You know, it might be a pretty wide range. It won't be as precise as like 42%, but it's more likely to be in the right range. And it might seem counterintuitive. If it's a wider range, how can it be more right? But it's about whether you're capturing the true number, right? So if you have to choose between these, in the context of research, it's about generalizing to populations, about estimating the absolute level of one variable at a time. You should choose a small but representative sample. Obviously, both would be better. A large representative sample is better, but to the extent that you have to pick one, representativeness is more important, in my opinion. And again, it'll depend on how tolerant you are of different kinds of error. But if you care about getting the right number, representative is better. Any questions? Okay, so in testing for differences, we pay attention to construct validity, internal validity, a little bit to external validity, but we often kind of just give it lip service, and statistical validity. In the context of generalizing to population, construct validity, external validity, and statistical conclusion validity. But remember, when you have to choose between a large sample or representative sample, choose a representative sample. Okay, now I probably will have confused you for this next quiz question. But in research, if people talk about a trade-off between external validity and something else, what are they most likely to be talking about? And I just gave you a different example than what I want to emphasize here, which is that it's usually internal validity. Usually the trade-off that people talk about the most is between external validity and internal validity, specifically doing a highly controlled lab study, which gives you good internal validity, but poor external validity, or less controlled field study where maybe you're observing rather than manipulating your predictor variable, but it's more realistic. That's the most common trade-off. It's not the only one, so we've talked about other trade-offs too, but that's a very common one. Because there's trade-offs basically among all of them, in research, you're often making trade-offs in design decisions. You could invest in a better measure, or you could invest in a larger sample, or you could invest in whatever. You know, time and money is finite. So very often we would want to use triangulation anyway. We want to do some studies where we're maximizing construct validity, but sacrificing a little bit somewhere else. Other studies where we might not have the best constructs. Like if you're adding, let's say a government does a survey of 40,000, a representative sample of 40,000 citizens every year, and you get to add a measure, but it has to be 30 seconds or less. So do you take that opportunity? Yes, you're sacrificing construct validity. You're going to have a less good measure than if they let you ask participants questions for 20 minutes, but you're going to get a representative sample, a large sample, et cetera. So you would do that study, but you would probably want to supplement it with a study where you have maybe a convenience sample, a less good sample of participants, but you could use the better version of the measure. And very often we can't have all of the things. So we need to triangulate, we need to be skeptical, make sure that we're interpreting things with their limitations in mind, and then seeing if the evidence points to something when we triangulate it all together. And so next week, we're going to talk about how to synthesize evidence and evaluate it together to try to come up with a conclusion, not just from a single study, but from a literature. So ultimately, we want all of the validities for a strong conclusion, but any researcher, any study where they tell you, we did great, we have no limitations, it's probably lying to you. I would go into it with a really healthy skepticism about the validities. I think that the threats to external validity are often the most obvious. We know that things might not generalize, that's usually quite clear. The threats to construct validity, you might need a lot of expertise to be able to detect if they measure the thing they say they're measuring, but sometimes it's on the face of it a ridiculous measure of the thing or manipulation of the thing. So for example, I remember reading a study where they were studying the effect of trauma on some dependent variable, I don't remember what. And they wanted to do an experiment because they wanted internal validity. And so what they did was they manipulated having a negative experience by giving the experimental group baking chocolate, unsweetened chocolate, and the control group got like good chocolate with sugar in it. And that was their manipulation of like a negative experience. And then they measured their dependent variable. And then they were making claims about the effect of trauma, operationalized as eating unsweetened chocolate. So you don't need a lot of expertise to know that that's a poor construct validity of that manipulation. They're not manipulating what they say they're manipulating. But it can be hard to assess construct validity. It can be hard to do it right. Internal validity, I think, is one of those where, again, I think common sense can take you quite a long way. Often people will make causal claims based on, say, measured variables, and they won't even discuss possible third variables, or they'll wave them away. And it doesn't take that much critical thinking to be able to come up with alternatives that are very plausible and a threat to them that they didn't consider or rule out. Statistical validity, I think, is probably the hardest, and it requires the most expertise to evaluate. And unfortunately, even experts evaluate it incorrectly and fool themselves into thinking that they have good statistical validity. They've eliminated the threats. They've reduced the chances of false positives by using a strict alpha, etc. When in fact they're fooling themselves, and you need to do a lot more digging to find the threat's statistical validity. So you need to assume that they might have done other things that they're not reporting, which can be really, really hard, and it can feel very harsh to assume that about researchers. And I can tell you as a journal editor, authors do not appreciate when I tell them that I think I can't rule out the possibility that you tried other things that you're not telling me about. They take that as an allegation about their character, when all I'm saying is we all do this and we don't even realize we're doing it. And so I think it's fair and necessary to assume that researchers are doing that unless they take the steps to show you otherwise. So unless they document everything transparently, report it transparently, you can see. And then even then, I wouldn't assume that they followed their plan. I would go and check, but at least they're letting you check their plan compared to what they did. And in fact, I would almost trust a result more if the results are messy. If there's some things that didn't quite work out, than if everything is perfect. Now, if it's too messy, sometimes they'll try to tell a story. One thing we're seeing now is people transparently reporting a set of studies where mostly it didn't work, but it kind of did over here. And then they tell a whole story about how it worked. It's like, well, thank you for showing me that actually it didn't. But your conclusion, like anyone who just skipped to the conclusion or just read the abstract would think it did work. So transparency is really great because it helps us be able to evaluate it more, but we still have to do the hard work of evaluating that transparency and coming to our own conclusions. Okay, so I hope that we've learned a lot of skills for evaluating individual studies, and then next week we'll talk about synthesizing individual studies and trying to come up with a conclusion. So I'll see you then.
Thank you.
Yeah, so you know